This video dives inside the factories that turned simple ingredients into world-famous ice cream. From Ben & Jerry's bold flavors to Dairy Queen's soft, serve precision, and Nestle's most popular products, we track the machines and quality controls that keep each scoop perfectly consistent. Today, we'll reveal how flavors are mixed, how textures are frozen, and how massive production lines deliver millions of cones every single day. Ben & Jerry's ice cream is produced by combining dairy and dry ingredients in a multi-stage mixing and freezing process that integrates inclusions and variegates at high precision. The process starts with the batching of the base mix, which is composed of whole milk, cream, liquid sugars, and dry solids such as stabilizers and emulsifiers. Milk and cream are pumped from cold storage tanks into insulated blending vessels. These vessels are jacketed for thermal control and fitted with slow-speed agitators. Liquid sucrose or invert sugar is added next through metered flow lines connected to bulk sugar tanks. Dry components, including milk powder, gore gum, and mono and diglycerides, are introduced through a powder induction system located at the top of the vessel. Powder is drawn into the vortex of the liquid mix through vacuum pressure and blended evenly by the impeller. Once fully blended, the base mix is transferred through sanitary piping to the pasteurization unit. Pasteurization is carried out using a high-temperature, short-time system where the mix is rapidly heated to a fixed temperature above 80 degrees Celsius. The heated mix is held in a thermal chamber for at least 25 seconds and then cooled immediately through a regenerative heat exchanger. This brings the temperature down to 4 degrees Celsius before the mix reaches the aging tanks. Aging tanks are insulated vertical silos equipped with slow-speed agitators to maintain mix homogeneity. The mix is stored here for a minimum of 4 hours and up to 24 hours depending on formulation. During aging, fat crystallization begins and proteins fully hydrate, which improves overrun stability and mouthfeel in the final product. After aging, the cold mix is pumped to the flavoring station. At this point, base flavor ingredients such as vanilla extract, chocolate liquor, or fruit puree are injected inline using precision dosing pumps. Each flavor component is calibrated to match the target formulation and is verified through flow sensors that monitor mass per second. From here, the flavored mix enters the continuous freezer. Continuous freezers are scraped surface heat exchangers that pump the mix through a cold barrel while simultaneously injecting air. The inner barrel surface is chilled using ammonia-based refrigerant and fitted with rotating scraper blades that prevent ice buildup. As the mix travels through the barrel, it begins to freeze on the walls and is continuously scraped into a fine frozen slurry. The injected air creates overrun, which determines the density of the ice cream. Overrun is adjusted by controlling the airflow rate and pump speed and is generally kept below 50% for super premium texture. Frozen mix exits the continuous freezer at a semi-solid state and enters the ingredient feed system. This system consists of a hopper that holds dry inclusions such as cookie chunks, brownie pieces, or chocolate chips. A positive displacement auger pulls inclusions from the hopper and meters them into the ice cream flow at a controlled rate. Each piece is fed in without breaking or melting due to the low product temperature and synchronized speed control. At this stage, variegates such as caramel swirls, fudge ripples, or peanut butter ribbons are also added. These are introduced through a separate pump system that deposits the variegate in a continuous stream alongside the ice cream stream. The product then passes through a laminar blending manifold that gently folds the components together without excessive shear. The structure of swirls is preserved using channelized flow paths that direct streams into the center of the bulk flow. The fully mixed and frozen product is directed to the filling station where pre-formed containers are loaded onto an indexed carousel. Each container is aligned with a filling head that dispenses a measured volume of ice cream. Fill rate is governed by a servo-controlled piston that maintains consistent deposit weight. Once filled, the container advances to a leveling station where a rotating plate smooths the surface of the product. Some variants receive additional toppings at this stage, such as crushed nuts or fudge drizzle, which are dispensed using vibratory feeders or rotary nozzles. Filled containers proceed to lidding, where high-speed arms place and seal plastic lids onto each pint. The lids are pressed down with calibrated force to create a friction seal. The sealed pints then move to the hardening tunnel, which is a spiral freezer maintained at temperatures below -30 degrees Celsius. The product remains in this tunnel for approximately 3 hours to achieve full core hardening. Cold air is forced over the pints at high velocity to extract latent heat uniformly. Upon exiting the hardening tunnel, the pints are conveyed to the coding station where batch information is printed on the lid or bottom using inkjet printers. Following this, the pints enter the cartoning system, where mechanical pushers insert them into printed cartons for multi-pack orders. For single packs, they are collated into crates using pneumatic actuators that align units for stacking. Each crate is conveyed to a palletizing station where robotic arms stack the product according to a programmed matrix. The pallets are then shrink-wrapped and labeled before being transferred to the frozen storage warehouse. Throughout the process, temperatures are continuously monitored and recorded at all key points, including mix tanks, freezers, hoppers, filling heads, and hardening zones. Every production step is automated using programmable logic controllers connected through an industrial network. Sensors measure flow rates, temperature profiles, viscosity, deposit weights, inclusion counts, and air pressure in real time. Adjustments are made automatically to maintain consistency across thousands of units per hour. The mix composition defines final mouthfeel and thermal behavior. Pasteurization ensures phase uniformity and emulsion stability. Aging promotes protein hydration and crystal growth. Freezing governs ice crystal size and air distribution. Inclusion delivery is timed precisely to avoid damage. Variegate folding is optimized for aesthetic and structural preservation. Product texture depends on water content, fat structure, and ice distribution. Overrun level directly affects scoop resistance and volume yield. Inclusion integrity depends on size, shape, and moisture content. Ripple distribution is determined by variegate viscosity and flow channel geometry. Final hardness is a function of exit temperature and hold time in the spiral freezer. Containers are designed to withstand both vacuum during filling and pressure changes during freezing. Lid placement requires precise tolerance to avoid deformation during hardening. Pallet loads are structured to prevent toppling and to allow airflow in the warehouse. All mechanical movements are synchronized to upstream and downstream operations to prevent backup or starvation in the line. Line cleaning occurs between flavor changes using automated clean-in-place systems that flush all internal surfaces with heated detergent followed by sterile rinse. Tanks, pipes, freezers, and filling heads are cleaned without disassembly using pressurized flow circuits. Wastewater is filtered and returned to treatment before discharge. No part of the Ben & Jerry's production process is manual once ingredients are loaded into storage tanks. Ingredient handling, dosing, mixing, heating, cooling, aerating, folding, depositing, sealing, hardening, coding, packaging, and stacking are carried out in a fixed sequence controlled by machine logic. Dairy Queen Soft Serve is created through a multi-phase process that begins with the formulation of a liquid dairy mix. The mix consists of milk solids, cream, sweeteners, stabilizers, and emulsifiers, which are combined in stainless steel batching tanks. The tanks are equipped with slow-speed agitators that maintain uniform suspension of all components during hydration. Milk and cream are pumped from chilled storage tanks using sanitary centrifugal pumps. Sugar is conveyed from bulk hoppers to the mixing tank via auger-fed systems. Stabilizers and emulsifiers such as mono and diglycerides, gargum, and carrageenan are introduced through powder induction ports. The dry ingredients are pulled into the vortex of the circulating liquid using a vacuum venturi system mounted above the mixing tank. The blended mix is agitated until all solids are hydrated and evenly distributed. Temperature in the mixing tank is gradually raised to above 65 degrees Celsius using a jacketed steam heating system. Once the desired blending temperature is reached, the mix is pumped to the pasteurization unit through insulated transfer piping. Pasteurization occurs using a plate heat exchanger which brings the liquid to 80 degrees Celsius or higher for a controlled retention time. After thermal treatment, the mix is cooled immediately to 4 degrees Celsius through countercurrent heat exchange. The chilled liquid is transferred to aging tanks, where it remains under gentle agitation for 8 to 12 hours. During aging, the fat particles begin to partially crystallize, which stabilizes emulsion and improves body and texture. Proteins and gums fully hydrate in this period, which enhances viscosity and mix performance during freezing. The aged mix is then directed to a homogenization unit. Homogenization is performed in 2 stages using a high-pressure valve assembly. In the first stage, fat globules are broken down by hydraulic shear at pressures above 1,500 pounds per square inch. The second stage ensures dispersion of remaining aggregates through pressure equalization at lower intensity. The homogenized mix achieves a uniform fat droplet size, which improves smoothness and prevents creaming. After homogenization, the base mix is cooled again to 4 degrees Celsius and held in refrigerated tanks until needed for production. When ready, the liquid is pumped to filling stations for intermediate packaging or loaded into distribution tanks if sent to retail locations. In stores, the liquid mix is fed directly into soft serve machines, which perform final freezing and aeration. The machines contain a freezing cylinder surrounded by a refrigerant coil. The mix is pulled from the refrigerated hopper into the freezing barrel using an auger system. As the auger rotates, it scrapes the interior barrel surface and simultaneously compresses the mix forward while incorporating air. Air is introduced through a calibrated orifice that meters flow based on pump rate. The ratio of air to mix is tightly controlled to produce the desired overrun, which is typically between 30 and 45%. This ensures a light texture without exceeding melt resistance limits. As the mixture moves through the freezing barrel, it begins to crystallize along the interior surface. Scraper blades continuously remove frozen product and fold it into the flowing stream. The barrel is chilled using a sealed system filled with R404A or similar food-grade refrigerant. The expansion valve regulates evaporator pressure to maintain a barrel wall temperature near -10 degrees Celsius. The partially frozen soft serve exits the cylinder at a semi-solid state with uniform aeration and consistent temperature. The product is dispensed directly from the extrusion nozzle into cones or cups using a gravity-fed or pump-assisted mechanism. Flow rate is controlled by a handle-actuated valve that opens a piston or gate at the nozzle outlet. The nozzle is shaped to produce the distinctive swirl pattern through laminar flow and rotational motion. The final product has a temperature near -6 degrees Celsius and maintains this state for several minutes under normal ambient conditions. No post-processing or hardening occurs after extrusion. Flavor variations are achieved through pre-flavored base mixes or inline syrup dosing. For syrups, a separate pump introduces concentrated flavor into the liquid stream before freezing. Syrup flow is matched to mix rate using flow meters and feedback control. Chocolate-dipped variants are produced by inverting the cone into a vat of liquid coating held at a fixed temperature. The coating solidifies upon contact with the cold, soft serve surface. The solid layer forms within 2 seconds due to the sharp temperature gradient and the high coconut oil content in the coating formula. Multi-flavor Twist products are created using a dual cylinder system. Each freezing barrel processes a different flavor. Both barrels feed a common extrusion head that contains 2 internal chambers. A Y-shaped nozzle merges the 2 flows at the outlet while maintaining separation. The twist effect is generated by the natural helical movement during downward extrusion. Inclusion-based variants, such as candy or cookie pieces, are added manually at the serving point. Toppings are not incorporated during freezing as they would interfere with scraper operation and pump integrity. Specialty formats, such as Blizzard products, use the same base soft serve dispensed into mixing cups. Solid inclusions are added from bulk hoppers and mixed using a vertical blender with a custom blade. The mixer agitates the entire volume briefly and evenly distributes solid inclusions without altering temperature or structure. The mix used for Dairy Queen soft serve has a fat content near 5% and milk solids non-fat between 11 and 12%. Stabilizers control ice crystal growth during freezing and maintain uniform viscosity during storage. Emulsifiers assist in fat dispersion and reduce weighing during freezing. Overrun is mechanically induced by synchronized air injection and auger transport. Storage tanks are cleaned with automated CIP cycles between production runs. Freezing cylinders are cleaned manually or with clean-in-place systems depending on model configuration. Syrup dosing systems are flushed with warm water after each flavor change. Coating vats are reheated and filtered periodically to maintain viscosity and clarity. All equipment involved in Dairy Queen production is constructed from stainless steel with hygienic welds and polished surfaces. Flow paths are sealed using tri-clamp fittings and silicone gaskets. Pumps use sanitary diaphragms or lobe rotors for gentle handling. Freezing units are maintained at fixed compressor settings based on product load and ambient conditions. The mechanical structure of the soft serve is defined entirely by air cell dispersion, fat matrix stability, and ice crystal size. Each parameter is determined by process inputs such as homogenization pressure, barrel residence time, and freezing surface temperature. No component of the product is batch frozen or aged at the point of service. Every portion is frozen continuously on demand and delivered immediately for consumption. Structural integrity is preserved through shear controlled mixing and precise overrun regulation. Nestlé ice cream production begins with bulk ingredient staging in temperature-controlled storage silos. Whole milk is held at 4 degrees Celsius in insulated stainless steel tanks fitted with agitators to prevent separation. Cream is stored separately in jacketed vessels and maintained at a consistent viscosity for accurate metering. Granulated sugar is housed in dry ingredient silos connected to the batching system via enclosed auger conveyors. Formulation is initiated by transferring milk and cream to the primary blending tank using positive displacement pumps with flow meters. The tank is jacketed and equipped with high shear agitators that disperse solids efficiently into the liquid phase. Sugar is dispensed from the silo using screw feeders that meter flow by weight. Dry milk solids are pulled into the tank through a Venturi adductor mounted on a recirculation loop. Stabilizers including guar gum and carrageenan are introduced as dry powders via a sealed hopper with rotary valve discharge. Once all components are loaded, the mix is agitated at low speed while steam is applied to the tank jacket to raise temperature to approximately 65 degrees Celsius. This step ensures solubilization of dry materials and begins the hydration of stabilizing agents. When the target temperature and viscosity are achieved, the mix is routed to the pasteurization system through a network of sanitary process piping. Pasteurization is carried out in a plate heat exchanger that subjects the mix to a thermal profile reaching 83 degrees Celsius. Holding occurs in a tubular section sized for 30 seconds residence time at peak temperature. The mix is then immediately cooled to 4 degrees Celsius using a countercurrent flow of chilled water or glycol solution. The cooled mix is sent to a set of aging tanks for further stabilization. Aging tanks are vertical silos fitted with slow-speed agitators to maintain uniformity without air incorporation. Mix resides in the tanks for a minimum of 4 hours and often up to 24 hours, depending on product formulation. During aging, the fat crystals begin to nucleate and proteins reach full hydration, which contributes to improved, overrun, and final texture. Before freezing, the aged mix is pumped through a high-pressure homogenizer that operates in 2 stages. The first stage uses a narrow orifice under 2,000 pounds per square inch to break fat globules into submicron particles. The second stage at reduced pressure eliminates aggregates to produce a fully dispersed emulsion. Homogenization ensures improved creaminess and resistance to fat separation during storage. Flavoring is performed in-line immediately before freezing using precision metering pumps. Flavor oils, cocoa solutions, coffee concentrates, and fruit essences are introduced via multiple injection ports into the flow stream. Flow sensors and control valves maintain exact volumetric dosing. Color additives are similarly introduced where required for specific variants. The flavored mix enters a continuous freezer, which consists of a horizontal, scraped surface heat exchanger. The interior barrel is cooled externally by a closed-loop ammonia system that maintains wall temperature below -25 degrees Celsius. The barrel is fitted with a rotating dasher that scrapes frozen product off the wall while mixing it with incoming liquid. Air is injected through a calibrated orifice located near the inlet, which determines the level of overrun. Overrun in Nestlé ice cream is typically maintained between 40% and 60% depending on the product line. The level of air is controlled by adjusting air pressure, dasher speed, and mix feed rate. Low overrun varieties are set below 40% for premium texture, while novelty products may be aerated to a higher extent for volume efficiency. As freezing proceeds, the product reaches a semi-solid state and exits the freezer through a pump that delivers it to the ingredient blending system. Solid inclusions, such as chocolate chunks, cookie dough pieces, fruit particulates, or caramel bits, are stored in hoppers above the blender. Each inclusion is gravity-fed into a feed auger that meters pieces into the ice cream stream in real time. The blending unit incorporates the inclusions into the flow path using horizontal paddles that avoid crushing fragile components. The feed rate of inclusions is electronically synchronized with the freezer output to maintain uniform distribution. Inclusion size and moisture content are tightly controlled to ensure structural integrity and to prevent bleeding or hardening after freezing. Products that require variegates such as chocolate fudge, caramel, or fruit syrup receive them at a second manifold downstream of the inclusion blender. A peristaltic pump draws variegate from a chilled tank and injects it through a fixed nozzle into the center of the ice cream flow. The pipe downstream is segmented to create controlled turbulence that folds the variegate through the product without mixing it completely. Once all ingredients are combined, the product moves to the filling station through a flexible insulated hose. Depending on the format, the product is filled into cups, tubs, cones, or novelty molds using piston fillers or rotary valves. For cups and tubs, the ice cream is deposited directly into pre-formed containers lined up on an indexing conveyor. Fill volume is precisely managed through a servo-controlled drive connected to the piston stroke length. After filling, surface leveling is performed by mechanical scrapers or rotating wipers depending on the container geometry. Some formats receive additional toppings such as syrup drizzles or solid garnish, which are deposited using vibratory trays or robotic arms. The containers then proceed to the lidding station, where lids are applied using pneumatic cylinders and heat or pressure sealing mechanisms. Filled and sealed units are then transferred into the hardening tunnel, which is a spiral or straight line blast freezer maintained at -35 degrees Celsius or lower. The air velocity within the tunnel is controlled by multiple high-speed fans and directed across the containers in a cross-flow pattern. Residence time in the hardening tunnel varies between 30 minutes and 3 hours, depending on product size and thermal load. During hardening, the unfrozen water content solidifies completely and the overrun structure becomes locked in place. Ice crystal growth is minimized by rapid freezing, which prevents graininess and ensures smooth texture. Hardening is considered complete when core temperature of the product reaches below -18 degrees Celsius. Once hardened, products are ejected from the tunnel and conveyed to the packaging line. For multi-pack items, individual units are collected into groups by mechanical diverters and placed into cartons by robotic pick-and-place systems. Cartons are formed from flat blanks using hot melt glue and folded by rotary formers. Cartons are coated with batch information using thermal inkjet printers. Carton product proceeds to case packing, where cartons are loaded into corrugated cases using side-load or top-load machines. Cases are sealed using tape or glue and labeled with destination and tracking codes. Finished cases are conveyed to automated palletizing stations, where they are stacked using articulated robotic arms onto wood or plastic pallets. Pallet patterns are selected by software based on carton size and unit weight to maximize stability and airflow in cold storage. Stacked pallets are shrink-wrapped with polyethylene film and transferred to blast freezers for holding before distribution. Final storage temperature is maintained at -28 degrees Celsius to -30 degrees Celsius with continuous airflow to prevent warm zones. The entire process from raw ingredient batching to final frozen storage is controlled by distributed PLC systems that communicate over industrial Ethernet. Parameters such as flow rate, temperature, pressure, inclusion count, overrun, and fill weight are monitored in real time. Feedback loops allow self-correction of dosing systems and line speed synchronization. No manual handling occurs at any stage after ingredient delivery. Ingredient silos, mix tanks, pasteurizers, homogenizers, freezers, blenders, fillers, tunnels, conveyors, and packers are all enclosed and automated. Cleaning is performed using clean-in-place systems that circulate caustic, acid, and rinse water through the entire process loop. Each product specification includes parameters for viscosity, Brix value, fat content, solids non-fat, pH, overrun, inclusion percentage, swirl concentration, core temperature, and packaging weight. All values are logged per batch and validated against product standards before release. Nestlé ice cream is defined by tightly regulated thermal transitions, physical dispersion of fat and air, inclusion integrity, and packaging precision. The resulting product has a defined melt curve, scoop resistance, and storage life, which are engineered through material control and mechanical process sequencing. No process stage is isolated or batch dependent beyond the initial mix. All subsequent steps are flow through and occur under continuous conditions to allow high throughput with minimal variation. Formulation changes are implemented by adjusting source tank routing and modifying pump set points. Multiple product lines operate in parallel using shared infrastructure with staggered schedules and automated changeovers. Flavor switching involves purging lines with heated water, followed by air blows and conductance verification before the next product introduction. Nestlé's frozen dessert output relies entirely on integration between thermodynamics, fluid mechanics, solids handling, and process control. Every movement and phase change contributes to the structural and sensory properties of the final packaged unit. Nutella biscuits manufacturing begins with production of the biscuit shell using a rotary molding and baking process. The biscuit dough is prepared by blending wheat flour with vegetable fats and powdered sugar inside a continuous horizontal mixer. The mixer operates at fixed low speed to prevent gluten development while ensuring even dispersion of fat particles across the flour. Water is added near the end of the cycle to activate binding. The dough is mixed until it reaches a defined plasticity suitable for molding and is then discharged into a feeding hopper connected to the forming line. The rotary molder presses the dough into engraved cavities on a rotating drum. The cavities have an open bottom design to release formed biscuits onto a steel mesh conveyor belt. The upper roller applies pressure to ensure full cavity fill, while the scraper removes excess dough and reintroduces it into the system. Each molded shell includes a circular depression designed to receive the Nutella filling after baking. The unbaked shells are spaced at regular intervals on the conveyor to allow for controlled baking conditions. The biscuit shells are conveyed into a multi-zone tunnel oven for baking. The tunnel consists of top and bottom heating elements, independently controlled in each zone. The oven temperature rises gradually from 160 to 210 degrees Celsius across the length of the tunnel. The baking profile is optimized to achieve full moisture removal from the dough without causing expansion or deformation of the molded cavity. Residence time in the oven is calibrated to match dough moisture content and thickness. Shells exit the oven fully baked with crisp structure and low residual humidity. After baking, the biscuit shells are cooled using ambient air directed across multiple conveyors arranged in a serpentine path to reduce surface and internal temperatures evenly. Cooling is required to stabilize the biscuit structure and prepare the cavity for Nutella filling. The biscuits are held at rest until their surface temperature falls below 30 degrees Celsius to prevent filling separation. In parallel, the Nutella filling is prepared in a high-shear emulsification unit. Using sugar, skimmed milk powder, cocoa, hazelnut paste, and vegetable oils. The ingredients are pre-mixed in separate feeders and metered into a blending vessel. The vessel operates under vacuum to remove entrapped air and maintain smooth consistency. The filling is processed at controlled temperature of 40 to 45 degrees Celsius to keep the viscosity within a defined range suitable for extrusion. Once homogenized, the filling is pumped to a filling head fitted with multiple nozzles. The cooled biscuit shells are conveyed under the filling head where each cavity is aligned with a single nozzle. A volumetric piston system injects the Nutella filling into each cavity with precise volume control. The fill level is calibrated to rise just below the edge of the biscuit wall to allow sealing with the top biscuit layer. After filling, the open surface is inspected for overflow or inconsistency using machine vision systems that communicate with rejection gates for off-spec product. A second biscuit layer is prepared using a similar dough mixing and molding process, but with a flat profile and no cavity. These flat biscuits are baked and cooled on a parallel line. After cooling, they are conveyed to the sandwiching station, where they are aligned and placed on top of the filled biscuit shells. Robotic arms or mechanical pushers perform the alignment and placement. Each top biscuit is pressed gently to create full contact with the Nutella surface, ensuring mechanical bonding through surface tension of the fat-based filling. The sandwich biscuits enter a brief setting tunnel where cool air is applied to solidify the outer edges of the filling. This step reduces movement during handling and packaging. The biscuits exit the tunnel with the Nutella core enclosed between two baked shells. Completed Nutella biscuits are conveyed to a wrapping line. Each biscuit is separated by timing belts and transferred to a horizontal flow wrapping machine. Printed film is pulled from a roll and formed into a tube by a forming collar. The biscuit enters the tube, and the machine applies a longitudinal heat seal using rotating pressure rollers. End seals are created using heated sealing jaws that cut and close the wrapper simultaneously. Wrapped units are transferred to a grouping station where multiple biscuits are oriented into lanes and grouped for final packaging. Mechanical pushers move the groups into pre-formed trays or cartons, which are closed and sealed using hot melt glue. Cartons are held under compression for a fixed time to ensure glue adhesion before being moved to the final packing area. Each element of the Nutella biscuit structure is formed in distinct production zones that operate in parallel and converge during assembly. The biscuit shell relies on controlled dough plasticity, consistent cavity shaping, and uniform baking to maintain its geometry. The filling requires stable emulsification and thermal regulation to maintain deposition quality and shelf stability. Assembly depends on mechanical alignment, volumetric precision, and sealing reliability. Material flow through the plant is linear with dedicated conveyance systems connecting each station. Biscuit shells and tops are kept on separate synchronized lines to ensure timing consistency during sandwiching. The filling pump rate and nozzle actuation are matched to biscuit speed to maintain throughput. Each station includes real-time sensors to monitor dough consistency, bake color, biscuit thickness, fill weight, and seal integrity. These sensors feed data to a central programmable logic controller that adjusts line speed, pump rate, and heating elements based on tolerances. The manufacturing of Nutella biscuits depends entirely on coordinated dosing, shaping, heating, cooling, filling, sealing, and wrapping processes. Every stage transforms the materials physically by temperature or mechanical force, without the use of molding or batch processing beyond the initial dough and filling prep. All thermal zones are closed-loop systems with adjustable airflow and temperature feedback. Air velocity, humidity, and direction are optimized to control baking profiles and cooling rates. These variables determine final texture and filling retention. Filling viscosity is adjusted by temperature control and shear rate. The shear thinning nature of the filling allows fast deposition while maintaining form when static. Deposit shape is retained until enclosed by the top biscuit and set during the cooling phase. Final product dimensions are defined by the cavity shape of the rotary mold and the flatness of the sealing biscuit. Mechanical indexing ensures positional accuracy for every fill and seal. No lateral shift is tolerated at the sealing station. The top biscuit must be seated with uniform pressure to prevent leakage or deformation. This step is controlled by pneumatic actuators that apply force within a calibrated range to prevent structural damage to the shell. The flat biscuit must align concentrically with the base. All scrap or off-spec products are diverted to return belts for reprocessing or rejection. These include unfilled shells, misaligned sandwiches, overfilled units, and wrapping errors. Each rejection path is physically separated to maintain uninterrupted flow of conforming units. Finished wrapped units pass a final weight check and metal detection station before secondary packaging. Cartons are printed, coded, sealed, and stacked for dispatch. No rework is conducted beyond primary quality rejection zones. Oreo production starts with the preparation of the chocolate biscuit dough using a high-capacity continuous mixer. Dry ingredients including soft wheat, flour, sugar, cocoa powder, and leavening agents are first weighed and fed into the mixing chamber. A separate line introduces palm oil or shortening, which is preheated to maintain fluidity and evenly distributed across the dry blend. Water is added gradually to initiate dough formation while mixing paddles rotate at low speed to prevent overdevelopment of gluten. The process continues until the dough reaches uniform consistency with defined plasticity suited for rotary molding. The mixed dough is conveyed to the forming system via an auger feed mechanism. The dough enters the hopper of a rotary molder, equipped with engraved rollers that define the embossed biscuit design. As the dough passes through the rollers, it is pressed into the cavities with precise pressure and then released onto a wire mesh baking band by means of a stripping knife. Excess dough is scraped from the roller surface and returned to the feed hopper for reuse. Biscuits are formed in continuous rows and spaced evenly to allow thermal exposure during baking. The molded biscuit pieces are carried into a multi-zone tunnel oven. The baking process is divided into sequential zones where temperature and air velocity are independently controlled. The oven begins at a moderate heat to set biscuit shape and rises to higher temperatures to complete internal baking and develop surface color. The typical baking curve ranges from 160 to 220 degrees Celsius. Each biscuit remains in the oven for 6 to 9 minutes, depending on thickness and moisture content. The mesh band allows uniform exposure to heated air on all sides. After baking, the biscuits are discharged onto a cooling conveyor where ambient air is directed from above and below to bring the temperature down gradually. The biscuits move across multiple levels or loops of conveyors to extend cooling time without occupying additional floor space. Final biscuit temperature is reduced to below 30 degrees Celsius to ensure structural stability before sandwiching. Simultaneously, the creme filling is prepared in a separate emulsification line. The filling consists of icing sugar, hydrogenated vegetable oil, soy lecithin, and flavoring agents. Ingredients are loaded into a planetary mixer equipped with high-speed blades and jacketed walls. The sugar is ground and combined with oil under shear to produce a smooth, homogeneous, fat-based paste. Temperature is maintained between 35 and 40 degrees Celsius to control viscosity and ensure pumpability. Once mixed, the filling is transferred to a holding tank fitted with agitators to prevent settling or phase separation. The cooled biscuits are conveyed into the sandwiching station in a synchronized line. They are separated into top and bottom rows using mechanical diverters. The bottom biscuits move directly under the filling depositor, while the top biscuits follow a delayed path to allow time for the filling application. The depositor contains multiple nozzles aligned with each lane of biscuits. Each nozzle dispenses a fixed volume of cream using a positive displacement piston pump. The deposit is placed at the center of each biscuit with consistent diameter and height. Top biscuits are aligned and placed onto the filled base biscuits by a pick and place mechanism. A servo-controlled arm picks the top halves and lowers them precisely onto the creme layer. The contact pressure is adjusted to spread the filling evenly without causing overflow. The result is a sandwich structure with a defined creme layer held between two embossed chocolate biscuits. Each finished sandwich is inspected for alignment and fill consistency using vision sensors and rejected automatically if outside tolerance. Sandwiched Oreos are then conveyed to the packaging section. The product flow is timed to match the entry speed of the horizontal flow wrapping machine. Wrapping film is unrolled and passed through a former to create a continuous tube. The Oreos enter the tube and are enclosed longitudinally using heated crimp rollers. Transverse end seals are applied using rotating sealing jaws that cut and seal each package simultaneously. Seal parameters are adjusted for film thickness and product temperature. The wrapped Oreos exit the machine in a sealed pillow pack configuration. Multiple wrapped packs are grouped into secondary packaging units using collection conveyors and counting gates. Depending on the product format, they may be stacked or aligned edge to edge and loaded into pre-formed cartons. Cartons are formed from flat blanks using folding arms and sealed with hot melt glue. Filled cartons are compressed briefly to ensure adhesive bond and discharged onto the final conveyor. Each line operates continuously, and is monitored by sensors that track biscuit position, deposit weight, package seal integrity, and material usage. The entire process is controlled by a centralized PLC system that coordinates line speed, temperature settings, pump pressures, and mechanical alignment across all stages. Biscuit texture is determined by dough moisture content, oven temperature profile, and baking time. Creme consistency is controlled through oil phase properties, shear rate, and deposition temperature. Assembly quality is a function of alignment precision, deposit accuracy, and pressure applied during sandwiching. Packaging integrity depends on film properties, sealing jaw temperature, and dwell time. Throughout Oreo production, no stage is batch-based beyond initial mixing. Dough and creme preparation feed into continuous mechanical systems that deposit, shape, bake, cool, fill, and wrap in a single linear sequence. Ingredient transformation is physical through heating, mixing, and compression. Structural integrity is achieved by thermal setting in the oven and mechanical bonding during sandwiching. The shape and weight of each Oreo are determined by the engraved mold cavities and the metered deposit volume. The embossed pattern is preserved by controlled dough texture and low expansion during baking. Biscuit brittleness is managed by adjusting water content and baking duration. Fill height is maintained by calibrating piston stroke length and pump cycle frequency. Every motion in the line contributes to dimensional uniformity and output consistency. Dough movement is regulated by roller speed and auger feed rate. Biscuit placement is defined by indexing and lane spacing. Creme application depends on nozzle diameter and internal deposit pressure. Sandwich closure requires precise Z-axis movement and timed application force. The rotary molding drum is cleaned automatically using scraper blades and air jets between production runs. Dough formulation is adjusted in real time based on humidity and flour batch variation. Viscosity of the cream filling is monitored using inline viscometers that signal temperature adjustments in the holding tank jacket. Oven parameters are logged continuously and used to regulate the baking curve. The production of Oreo cookies involves multiple heat and shear-based unit operations that alter physical properties without any fermentation or leavening beyond minor chemical agents. All dimensions are mechanically imposed and retained by careful control of thermal transitions and compression events. No rework is introduced into the sandwiching process. Only biscuits that meet shape, color, and thickness criteria are accepted. Filling rejects are filtered back into the holding tank through a return line. Packaging errors are removed before sealing to prevent final product contamination. The system is designed to maintain flow and reject outliers without stopping. The final Oreo structure consists of 2 rigid outer shells and 1 malleable creme layer. The shells resist deformation under handling. The creme adheres without fluid migration. Moisture barrier properties are maintained by the biscuit's low water activity and the hydrophobic nature of the fat-based filling. Nutter butter cookie production begins with the preparation of the peanut-flavored dough. Dry base materials are loaded into a large capacity horizontal mixer through automated dosing systems. These materials include soft wheat flour, granulated sugar, dextrose, baking soda, salt, and peanut flour. Separately, hydrogenated vegetable oil and peanut butter are preheated in jacketed holding tanks to reach a flowable state. The fats are pumped into the mixer and distributed over the dry mix, while the paddles rotate at low speed. Water is then injected into the chamber through spray nozzles to activate hydration without overdeveloping gluten. Dough temperature is maintained between 18 and 22 degrees Celsius. The dough is mixed until a target plasticity is achieved, ensuring it can be molded without sticking or tearing. Once complete, the dough exits the mixer via a discharge chute and is conveyed to a dough feed hopper mounted above a rotary molder. The molder is equipped with engraved rollers featuring the signature peanut shell pattern and split mold design that will define the top and bottom cookie pieces of the Nutter Butter sandwich. As the dough is fed into the rotary molder, the engraved drum compresses and shapes the dough into uniform cookie halves. A fixed scraper blade removes excess dough from the roller's surface, while a vacuum-assisted mechanism ensures accurate demolding from the cavities. Formed cookies are transferred onto a wire mesh conveyor belt that transports them through a continuous tunnel oven. Excess dough is rerouted via a return auger and refed into the forming system. The tunnel oven is divided into sequential thermal zones with independent temperature control. The initial zone sets the cookie shape at approximately 160 degrees Celsius. The intermediate zones raise temperature to 200 degrees Celsius to drive off internal moisture. The final zone applies finishing heat at 220 degrees Celsius to develop the surface texture and light browning. Airflow direction and volume are adjusted separately for top and bottom heating across all zones. The wire mesh belt permits full convection exposure around each cookie piece. Total baking time ranges from 6 to 9 minutes depending on dough moisture, product thickness, and belt speed. During baking, moisture content is reduced from around 18% to below 2%. The cookies exit the oven fully formed and structurally rigid. They are conveyed to an ambient cooling system composed of multi-tiered belts with forced air circulation. Cookies must reach below 30 degrees Celsius before proceeding to filling. While the cookies cool, the peanut butter creme filling is produced in a separate, continuous emulsification system. The formulation includes icing sugar, hydrogenated vegetable oil, roasted peanut paste, salt, and emulsifiers such as mono and diglycerides. The ingredients are metered into a vacuum mixer fitted with high-speed rotating blades. The mixer maintains low pressure to prevent air incorporation, while the fat and sugar blend into a smooth paste. Product temperature is held between 38 degrees Celsius and 42 degrees Celsius to control viscosity and ensure deposit stability. The filling mass is pumped from the mixer into a stainless steel holding tank equipped with a slow agitator to maintain consistency. From there, the creme is fed through a positive displacement pump into a volumetric depositor that sits above the sandwiching conveyor. Cooled cookie halves are divided into bottom and top rows using a mechanical separator with indexed belts. The bottom halves are aligned and conveyed beneath the depositor. Each nozzle in the depositor corresponds to one cookie lane. As each cookie passes below, a metered quantity of peanut creme is dispensed onto the center of the bottom cookie surface. The deposit rate is synchronized with belt speed to maintain consistent fill weight and location. Top cookie pieces are then aligned with their corresponding filled bottom halves using a mechanical alignment rail. A pusher bar or servo-driven actuator lowers each top cookie onto the filling. The applied pressure is controlled to spread the filling to the desired diameter without squeezing it beyond the edge. The resulting sandwich maintains clean fill lines and full bonding across the contact surface. Assembled Nutter Butter sandwiches are conveyed through a short resting belt to allow any residual filling movement to stabilize. From there, they move into the packaging system. The first packaging stage consists of a flow wrapping machine fed by a timing belt that spaces cookies at fixed intervals. Wrapping film is unwound from large rolls and formed into a tube around the cookies using a forming collar. The longitudinal seam of the wrapper is sealed by heated crimp rollers, while the ends are cut and sealed by rotary jaws. Temperature and dwell time of the sealing jaws are set based on film thickness and line speed. The wrapped cookies exit the flow wrapper as individual units or twin packs depending on the product variant. Wrapped units are conveyed to a grouping system where multiple cookies are collected and inserted into multi-pack cartons. Mechanical pushers or robotic pick-and-place arms load the cookies into pre-glued cartons. Cartons are sealed using hot melt adhesive applied by contact nozzles. Glue setting is ensured by compression flaps and a short dwell section. The cartons are then labelled, coded, and discharged to case packing. Throughout the process, all movements are continuous and synchronized. Dough feed, forming, baking, cooling, creme preparation, depositing, sandwiching, and wrapping occur without manual intervention or batch holding. Each station is linked to upstream and downstream processes by belt conveyors, sensor arrays, and real-time control systems. The final texture of the Nutter Butter cookie shell depends on dough fat content, moisture level, forming pressure, and thermal profile. The filling spread and adhesion characteristics are governed by shear during mixing, fat phase structure, and filling temperature at deposition. The sandwiching step relies on timing and vertical alignment accuracy to avoid rotation or breakage. Rework is minimized through inline inspection at multiple points. Cookies with incomplete molding, overbake, off-center filling, or misalignment are removed by air rejection systems or diverted for grinding and remelting. Only fully conformed products proceed to final packaging. The design of the peanut shell shape is retained through rigid cavity molding, low dough expansion, and short baking time. Each cavity in the mold drum is precision machined to micron level tolerances. The emboss pattern depth controls final surface visibility. The moisture balance in the dough ensures sharp edge retention and minimal slumping during oven transit. The filling deposit pattern is a function of nozzle diameter, piston stroke length, deposit speed, and creme viscosity. The diameter of the final fill is determined by vertical pressure from the top cookie and the flow behavior of the fat matrix. The ratio between shell weight and filling weight is maintained within narrow limits to ensure structural integrity and mouthfeel. Line efficiency is governed by synchronization between forming rate, baking throughput, and filling capacity. Adjustments to belt speed, oven temperature, or depositor cycle timing propagate downstream. Any mismatch between stations can result in underbake, inconsistent fill, or packaging misfeeds. The mechanical layout of the Nutter Butter production line is linear and modular. Dough flows from mixer to molder. Biscuits flow from molder to oven. Creme flows from mixer to depositor. Sandwiches flow from depositor to wrapper. Each segment includes buffer zones to absorb variation and maintain steady output. Packaging formats can be switched by adjusting forming jaws, wrapping film feed width, and carton loader configuration. Line reconfiguration is managed through digital interfaces that adjust motion profiles, material flow paths, and spacing intervals. The final Nutter Butter product consists of 2 molded peanut-flavored cookies bonded with a central layer of smooth peanut butter creme. The top and bottom shells are symmetrical and embossed with the same pattern. The cream layer is centered and flush with the cookie edge. The finished unit exhibits uniform thickness, aligned sandwich halves, and sealed packaging with fixed weight. Each unit operation transforms the ingredients through shear, heat, pressure, cooling, or extrusion. No fermentation or chemical expansion occurs. All structural characteristics are mechanically imposed and thermally locked. The line operates at a continuous pace of thousands of cookies per hour. Consistency across units is maintained by regulating every input condition, from ingredient feed to forming pressure to deposit rate. All cookies follow the same linear path through the same physical conditions. The result is a uniform, mass-produced sandwich product with no variation in shape, weight, or filling distribution. M&M's production begins with the manufacturing of the chocolate core. Each milk chocolate center is formed by molding a precise deposit of tempered chocolate onto a cooling belt. Chocolate mass is created by blending sugar with cocoa liquor and milk solids in a high-capacity mixer. This blend is refined through a 5-roll mill that reduces particle size to below 30 microns. The refined paste is moved to conching tanks where it is mixed and aerated at a temperature of 55 degrees Celsius. Lecithin is added as an emulsifier to achieve a smooth, flowable texture. The conched chocolate is held in jacketed tanks to maintain a liquid state. It is tempered using a 3-stage tempering unit which cycles the chocolate through controlled heating and cooling to form stable crystal structures. Tempered chocolate is pumped to a depositor that releases metered drops onto a stainless steel belt moving through a cooling tunnel. The belt temperature is kept between 5 and 10 degrees Celsius to solidify the chocolate in less than 60 seconds. The formed centers are demolded mechanically and stored in buffer bins before the next process. For peanut M&Ms, the process begins by dry roasting raw peanuts in continuous belt roasters. Roasting temperature is maintained at 160 degrees Celsius for 20 minutes. Peanuts are then cooled by ambient air in a vibrating cooler. After cooling, they pass through a sizing unit that removes undersized or broken nuts. The selected peanuts are fed into panning drums where chocolate is applied in successive layers. Each drum rotates at a fixed angle and speed to ensure uniform tumbling. A measured amount of chocolate is sprayed onto the surface of the peanuts using heated nozzles. After each application, cold air is blown into the drum to partially solidify the layer. This process repeats until the peanuts reach a target diameter. The final chocolate coating is smoothed using a polishing pass with minimal chocolate to eliminate surface irregularities. Crispy M&Ms are built around an extruded rice core. Rice flour and corn grits are mixed with water and processed through a twin-screw extruder. The extruded dough is cut into uniform pellets using a rotating blade. Pellets are puffed in a high-temperature expansion chamber. After expansion, they are dried in a convection dryer, then coated with a thin film of fat to reduce moisture absorption. The puffed cores are enrobed in chocolate using the same panning method applied to peanuts. All chocolate-coated centers are transferred to the sugar coating area. The process starts in large rotating pans where the cores are sprayed with a sugar solution. The sugar syrup consists of sucrose water and glucose and is delivered at a constant temperature of 75 degrees Celsius. Each spray cycle is followed by a drying cycle that circulates dehumidified air around the rotating bed of centers. Sugar builds up in fine layers over dozens of cycles. The panning operator adjusts spray volume drum rotation speed and airflow to maintain uniformity. Once the sugar shell reaches the desired thickness, color is applied. Coloring is done by mixing food dye with shellac and carnauba wax to produce a glossy, tinted coating. The colorant is misted onto the sugar-coated centers in a fine spray. Multiple passes may be required for dark colors like red or brown. After coloring, the coated pieces are polished with a dry mixture of shellac and wax. This step is performed in polishing pans, rotating at low speed. The polishing agent adheres to the surface and is distributed by friction between the tumbling pieces. The resulting finish is smooth, hard, and glossy with highlight reflectivity. Polished M&Ms are discharged from the pans and moved to a conditioning silo. This silo is temperature and humidity controlled to allow the coating to fully harden and stabilize. Residence time in the silo is typically 2 to 4 hours depending on coating thickness. After conditioning, the candies are conveyed to the printing station. The iconic letter is applied using offset graver printers. Each piece is positioned in a dimpled conveyor plate with cavities sized to hold one candy. The plate passes beneath a print head which uses edible white ink. The print roller is engraved with the letter M and rotates in sync with the conveyor. Contact pressure is controlled pneumatically to ensure legibility without damaging the shell. Printed candies are inspected by machine vision systems that detect missing or malformed prints. Unmarked units are removed by air jets and recycled into the system for reprinting. Approved units continue to the packaging stage. The candies are weighed and dosed using multi-head combination weighers that drop exact quantities into vertical form fill seal machines. Packaging film is pulled into the forming collar and sealed into a tube. The bottom is sealed with a heated jaw and the product is dropped in. The top seal is then applied, creating a pillow pack. Filled packages are conveyed to check weighers that verify compliance with weight specifications. Any over or underweight packs are removed automatically. From start to finish, the process involves sequential mechanical operations that include mixing, depositing molding panning, spraying printing, and sealing. Each unit operation is tuned to specific parameters that ensure dimensional consistency and coating integrity. The manufacturing line is modular, with separate zones for chocolate handling, core preparation, sugar coating, and final packaging. Mass flow is maintained using belts, pneumatic conveyors, and elevators that transfer product between levels. The entire line is integrated by a control system that monitors temperature, flow rate, viscosity, and speed at each point. Adjustments are made automatically through feedback loops that maintain constant output. There are no batch holds once the system is running. The chocolate centers flow continuously through coating, coloring, and packaging without pause. Sugar solutions are replenished through a bulk feed system with inline heating and mixing. Chocolate is tempered in a loop with real-time viscosity monitoring. Each candy undergoes a transformation that begins with a molten mass and ends with a layered composite structure. The core is solid or puffed depending on type. The first layer is tempered chocolate applied by drum enrobing. The second layer is crystalline sugar formed by sequential syrup application and drying. The third layer is colorant and wax forming the glossy finish. The fourth step is marking with the printed letter. All coating is additive applied in micro-thin layers, controlled by time rotation and fluid volume. There is no molding of the outer shape. The spherical form is achieved through cumulative coating and mechanical tumbling. The smoothness is the result of abrasion polishing and repeated layering under rotation. Thermal inputs are limited to chocolate tempering, syrup heating, and ambient conditioning. No baking, frying, or high temperature processing occurs. Moisture is carefully controlled during sugar coating to avoid bloom or crystallization defects. Every part of the process is dry, except the syrup spray and initial chocolate melt. Mechanical design of the panning drums ensures even exposure for each piece. Drum material is stainless steel with ribbed interiors that increase mixing efficiency. Air delivery systems are connected to each drum to maintain controlled drying. The air is filtered, cooled, and dehumidified before being directed at the product. Timing across the system is synchronized by programmable logic controllers. Every depositor, cutter, printer, and packager is indexed to match upstream flow. Any stoppage triggers a cascading halt to preserve continuity. Materials are buffered at key points to allow restart without waste. Twix production begins with controlled preparation of the biscuit base that defines the structure of the bar. Twix biscuit dough is created by feeding wheat flour into a continuous mixing system. The flour is combined with sugar and vegetable fat inside a horizontal mixer. Mixing paddles rotate at low speed to coat flour particles with fat. Water is added in measured flow to bind the mixture into a cohesive dough. Dough temperature is regulated to maintain firmness during shaping. The mixed dough exits the mixer and enters a feed hopper that supplies the forming line. The dough is transferred onto a rolling table, where compression rollers flatten it into a continuous sheet. Roller gap settings determine final biscuit thickness. The sheet passes through alignment guides that maintain straight edges. A rotary cutting drum imprints the dough into uniform rectangular segments. Excess dough is removed and recycled upstream. The shaped dough pieces are placed onto a steel mesh conveyor for baking. The baking stage uses a tunnel oven with multiple heating zones. The conveyor transports dough pieces through gradually increasing temperatures. Initial zones dry the surface without browning. Middle zones promote internal structure development. Final zones create golden coloration and crisp texture. Oven airflow is directed above and below the conveyor. Baking time is adjusted to control moisture content. The baked biscuit bases exit the oven with stable shape and strength. Freshly baked biscuit bases move directly into a cooling tunnel. Ambient and chilled air flow reduces biscuit temperature. Cooling prevents caramel deformation during later stages. Conveyor speed maintains spacing between pieces. The biscuits emerge cooled and rigid. They are aligned into lanes for caramel application. Caramel production occurs in a separate continuous system. Glucose syrup flows into a preheating chamber. Milk solids and sugar are added under agitation. The mixture passes through a vacuum cooker. Reduced pressure lowers boiling temperature. Moisture evaporates rapidly to thicken the caramel. Cooking parameters define final viscosity. The caramel exits the cooker as a smooth, elastic mass. Cooked caramel is transferred into a holding vessel. Slow agitators prevent crystallization. The caramel is pumped through heated pipes to the depositor. The depositor contains multiple nozzles aligned with biscuit lanes. Each nozzle dispenses a precise ribbon of caramel. Deposition rate controls caramel height. Temperature ensures proper flow and adhesion. Caramel-coated biscuits move through a setting tunnel. Cool air partially solidifies the caramel layer. The caramel becomes firm enough to hold shape. The biscuits continue along the conveyor without distortion. The caramel surface remains tacky for chocolate bonding. Chocolate coating begins with preparation of milk chocolate. Cocoa mass, sugar, milk powder, and cocoa butter are blended. The mixture is refined to reduce particle size. Conching develops smooth texture. Finished chocolate is transferred to tempering units. Tempering controls crystal formation. Chocolate reaches a stable liquid state. Tempered chocolate flows into the enrobing machine. A continuous chocolate curtain forms across the conveyor. Biscuit caramel assemblies pass beneath the curtain. Chocolate coats the top and sides evenly. A bottoming system coats the underside through the mesh belt. Excess chocolate drains back into the system. Air knives shape the chocolate layer. Gentle vibration removes bubbles. The coating thickness becomes uniform. Decorative surface lines may form naturally from airflow. The enrobed Twix bars enter a cooling tunnel immediately. Cooling tunnels use staged temperature zones. Initial zones prevent surface cracking. Later zones fully crystallize the chocolate. Air velocity ensures even cooling. Belt speed defines dwell time. The chocolate shell hardens around the biscuit and caramel core. After cooling the bars, exit with rigid structure. The bars are transferred to the splitting station. Twix bars are cut lengthwise into twin fingers. Servo-controlled blades ensure precise separation. Each finger maintains identical dimensions. Separated Twix fingers are aligned on packaging conveyors. Spacing belts organize the flow. The bars enter flow wrapping machines. Packaging film is fed from large rolls. The film wraps around each finger. Longitudinal seals are formed by heated rollers. End seals are created by rotating jaws. Wrapped fingers are paired for twin pack format. Collation belts bring two wrapped fingers together. The paired unit is wrapped again or inserted into an outer sleeve. Wrapping speed matches upstream production. The sealed packs exit the line in continuous flow. Throughout Twix, manufacturing every step is synchronized. Conveyor speeds coordinate with deposition rates. Thermal stages are sequenced to avoid overlap. Mechanical forming ensures consistent geometry. Material flow remains uninterrupted from dough to wrapper. The biscuit base provides rigidity. The caramel supplies chew and adhesion. The chocolate delivers coating and protection. Each layer is applied in a defined order. Temperature control maintains layer integrity. Timing ensures bonding without deformation. Twix production operates as a linear system. Dough shaping precedes baking. Baking precedes caramel deposition. Caramel setting precedes chocolate enrobing. Chocolate cooling precedes cutting and wrapping. Each stage depends on the previous one. Ingredient transformations are mechanical and thermal. Dough changes through heat exposure. Caramel thickens through evaporation. Chocolate crystallizes through controlled cooling. No stage reverses a previous transformation. The biscuit sheet thickness defines bite texture. Caramel viscosity defines chew resistance. Chocolate thickness defines snap. These variables are adjusted through machine settings. No manual shaping occurs after initial dough forming. Continuous monitoring of belt alignment prevents product drift. Sensors maintain spacing accuracy. Pump pressures control flow stability. Roller speeds define forming precision. Each parameter is linked to output consistency. Twix bars emerge fully assembled before packaging. The layered structure remains intact. The product shape remains constant across units. The manufacturing line produces thousands of bars per hour. Output remains uniform due to synchronized automation. Every Twix bar follows the same physical path. Raw materials enter as powders and liquids. Finished bars exit as layered chocolate products. The process relies on controlled movement. Thermal transitions define each stage. Mechanical handling preserves structure. Snickers bars are built in layers, starting with the nougat foundation. The nougat is produced by combining sugar, corn syrup, and milk powder in a heated mixing vessel. These ingredients are blended and cooked until they form a thick paste. A separate stream of whipped egg whites is prepared using high-speed beaters. The aerated egg white mass is gradually folded into the hot sugar mixture. This step introduces air cells and creates the spongy texture of the nougat. The blending continues until the mixture reaches uniform density and viscosity. The final nougat mass is held in a feed tank equipped with slow paddles to prevent collapse. The nougat is deposited as a continuous slab onto a moving belt. The belt is lined with a non-stick material to allow clean release. A leveling roller spreads the nougat to the target height. Guide rails control the slab width. The slab is conveyed into a cooling chamber to set the structure. Chilled air circulates around the slab until surface temperature drops below 15 degrees Celsius. The cooled nougat slab exits the chamber with a firm texture and is ready for the next layer. Caramel is prepared in a separate cooking line using glucose syrup, milk fat, and sucrose. These ingredients are fed into a continuous cooker with steam-heated zones. The mixture is heated to reduce water content and initiate Maillard reactions. Caramelization develops flavor and viscosity. The cooked caramel exits the vacuum chamber and enters a holding tank. The tank is agitated slowly to maintain homogeneity and prevent crystallization. The caramel temperature is maintained near 60 degrees Celsius for optimal flow. Roasted peanuts are prepared separately. Raw peanuts are roasted in a forced air roaster where temperature is held between 160 and 180 degrees Celsius. Roasting continues for 20 minutes until internal moisture falls below 2%. The peanuts are cooled by ambient air, then passed through a vibrating grater. Oversized and broken peanuts are removed. The accepted peanuts are stored in silos connected to the deposition system. Caramel is deposited onto the cooled nougat slab using a curtain-style applicator. The applicator spans the full width of the slab and releases caramel in a uniform layer. Flow rate and belt speed are adjusted to control caramel thickness. Directly after caramel application, roasted peanuts are dropped from a vibratory feeder. The feeder spans the same width as the slab. A controlled quantity of peanuts is dispensed and embedded into the caramel by a light compression roller. This roller presses the nuts into the surface to ensure mechanical bonding. The multi-layer slab is conveyed through a second cooling tunnel. The tunnel has temperature zones starting at 12 degrees Celsius and ending at 6 degrees Celsius. Chilled air is circulated above and below the belt to harden the caramel. Dwell time is calibrated to match the slab thickness and maintain shape stability. The slab exits the tunnel with a cohesive structure and defined layers. A guillotine cutter slices the multi-layer slab into narrow lanes. The cutter uses servo-controlled blades aligned with the slab width. The lanes are transferred onto narrower belts for portioning. Another guillotine cuts the lanes into bar-length segments. Blade speed and belt speed are synchronized to ensure uniform bar size. Each segment is now a complete core containing nougat, caramel, and peanuts. The bar cores are spaced and oriented for enrobing. They enter the chocolate coating system in a single file. Milk chocolate is melted in a jacketed tank and tempered in a continuous flow unit. The tempering process includes heating to melt all crystals, cooling to initiate stable crystal formation, and reheating to a precise working temperature. The tempered chocolate flows into a pump system that feeds the enrober. Each bar passes under a chocolate curtain that coats the top and sides. The base of each bar contacts a chocolate-coated roller or is sprayed from below. Chocolate flow is adjusted by modifying pump speed and curtain width. Excess chocolate is removed by a vibrating section that shakes the belt gently. Air knives apply a controlled stream of air to smooth the surface and reduce buildup. The coated bars enter a cooling tunnel to crystallize the chocolate. The tunnel has multiple zones with decreasing temperatures. Airflow is directed to maintain even cooling without condensation. The bars are conveyed for a fixed duration to complete the chocolate setting process. The final chocolate shell is solidified and stable upon exit. Each Snickers bar is now fully assembled and coated. Bars are aligned for wrapping using guiding rails and spacing conveyors. Flow wrappers are fed with printed film from a reel. The film is shaped into a tube around each bar. Heat sealing rollers create the longitudinal seam. Rotating jaws apply end seals. Seal pressure and temperature are monitored to match film type. The wrapped bars are conveyed into collection bins or directly to packing systems. Depending on product format, bars may be grouped into single, twin, or multi-pack configurations. Grouping conveyors align the bars into sets. Mechanical pushers or robotic arms load the grouped bars into cartons. Cartons are formed from flat blanks and glued using hot melt adhesive. Cartons are closed and sealed at the final station. No manual intervention is used during shaping, layering, cutting, or wrapping. All movements are performed by synchronized mechanical systems. Sensors monitor product position and spacing. Feedback loops adjust flow parameters. Each bar follows the same linear path from ingredient feed to final wrap. Nougat provides internal volume and structural support. Caramel binds the peanuts and delivers chew. Peanuts create inclusion texture and flavor variation. Chocolate forms an outer shell that locks the layers in place. Each component is manufactured and applied in discrete steps. Thermal and mechanical conditions are optimized for each transition. The slab format enables high-speed processing. Layering occurs in continuous motion. Cooling is integrated between each stage to preserve geometry. Cutting is servo-synchronized to belt speed. Chocolate tempering is calibrated to match bar throughput. Wrapping systems operate at matched cadence to upstream enrobing. Ingredient flow is regulated by volumetric pumps, gravity feeders, and temperature-controlled tanks. Mixing occurs in closed vessels with integrated agitators. Heat is applied via indirect steam or electric jackets. Each process vessel is isolated by flow valves and sensors. Conveyor systems link every step of the process. Belt widths and speeds are chosen to prevent jamming and maintain alignment. Transfer points are angled to reduce impact and preserve bar shape. Side guides and rollers keep products centered. Accumulation zones provide buffer capacity between stages. The system supports continuous operation without backtracking. Each bar is formed from base to wrap in a single direction. Mechanical shaping precedes deposition. Deposition precedes cutting. Cutting precedes coating. Coating precedes cooling. Cooling precedes wrapping. Every phase transforms material by specific mechanical or thermal means. Mixing combines dry and wet. Cooking removes water. Depositing creates form. Cooling fixes structure. Cutting defines unit size. Enrobing applies the shell. Wrapping seals the finished form. Peanut butter production begins with the bulk intake of raw, shelled peanuts delivered in containers or silos. Peanuts are gravity-fed into hopper systems equipped with vibratory feeders that control the rate of flow into the cleaning section. Cleaning involves sequential mechanical separation units, including air classifiers, rotary drum screens, and gravity tables. Air classifiers remove lightweight debris using high-velocity airstreams. Rotary screens separate based on particle size, discarding small fragments, sticks, and foreign seeds. Gravity tables use differential vibration and airflow to isolate denser whole peanuts from lighter defective material. Cleaned peanuts are transferred via bucket elevators into temporary storage bins prior to roasting. Roasting is carried out in continuous belt roasters or rotary drum roasters depending on line capacity. Peanuts are conveyed in a single layer through a thermal tunnel with forced hot air. Drum roasters use direct heat combined with rotating tumbling action. Roasting temperature ranges from 160 degrees Cs to 180 degrees Cs, with residence times of 25 and 40 minutes. Moisture sensors at the exit point ensure target moisture reduction to below 2%. Roasting also develops flavor and reduces microbial load. Cooled air is forced across the roasted peanuts immediately upon exit. Cooling conveyors equipped with perforated belts and axial fans reduce peanut temperature to below 35 degrees Celsius to prevent oil migration or condensation. Peanuts are held in cooled hoppers with agitation to prevent bridging before entering the blanching process. Blanching removes the outer skin and splits the peanuts. This is performed in two ways: dry blanching or water blanching. Dry blanching involves friction rollers that rub off the skins as peanuts pass through serrated cylinders. Water blanching involves immersion in hot water, followed by belt conveyors fitted with rubber rollers. In both methods, skin fragments are removed by aspiration or vacuum collection systems. Split peanuts pass through inspection belts or optical sorters to remove discolored, moldy, or damaged halves. High-speed cameras scan each peanut and trigger air jets to divert off-spec material. Sorted peanuts are collected in surge hoppers and metered into grinders. Peanut grinding is performed in two stages: primary size reduction and emulsification. The first stage uses a hammer mill or disc attrition mill. Peanuts are fed into a chamber with rotating blades or abrasive plates. The initial grind reduces particle size to around 300-500 microns. The paste is then pumped into a second stage colloid mill. The colloid mill performs high shear homogenization between a rotor and stator, reducing particle size to below 100 microns. Rotor speeds exceed 3000 RPM, and the grinding gap is adjustable for texture control. The grinding process also generates frictional heat, raising product temperature to 60-80 degrees Celsius, which reduces viscosity and facilitates emulsification. During the second stage grinding, or immediately afterward, stabilizing agents and additives are introduced. Common stabilizers include fully hydrogenated vegetable oils, such as rapeseed or cottonseed oil. These are pre-melted in jacketed tanks and dosed using heated transfer pumps. Stabilizer addition typically ranges from 1 to 2% by weight and is controlled with flow meters. For sweetened or flavored varieties, additional ingredients such as sugar, salt, molasses, or cocoa powder are added through powder feeders or liquid dosing pumps. These materials are pre-weighed and incorporated in line using dynamic mixers with static mixing elements or turbine blades to ensure rapid dispersion into the viscous peanut paste. After additive incorporation, the peanut butter undergoes a degassing phase. The hot paste is transferred to a vacuum chamber or degassing tank where air bubbles are removed. The system applies vacuum pressure between 0.7 and 0.9 bar while slowly agitating the product to avoid entrapping more air. This step improves texture and packaging stability. Degassed product flows into surge tanks equipped with slow-speed agitators and thermal jackets to maintain fluidity. Temperature is held between 55 to 65 degrees AS to facilitate downstream handling. Product is then directed toward the packaging line via sanitary lobe pumps, which provide high volume transfer without shear. Before filling, the peanut butter may be passed through a scraped surface heat exchanger to adjust temperature precisely. The system uses rotating scraper blades inside a jacketed tube to maintain heat transfer efficiency without fouling. Outlet temperature is held constant, typically 50-55 degrees Celsius, for optimal flow into containers. Packaging is performed on high-speed, servo-driven filling lines. Empty jars made of PAT or PP plastic are depalletized and placed onto the conveyor. Each jar passes through an ionized air rinser that removes particulate matter. Clean jars are indexed into a rotary filler with multi-nozzle heads. Volumetric piston fillers or mass flow filling systems dispense precise quantities of peanut butter into each jar. Fill levels are controlled within plus 0.5% tolerance. Nozzles are heated or jacketed to prevent clogging due to cooling product. Some systems use bottom-up filling to prevent air entrapment and surface voids. After filling, jars proceed to the capping station. Caps are sorted and aligned using centrifugal feeders or vibratory bowls, then applied and torqued by rotary chuck cappers. Torque sensors monitor seal integrity, and improperly sealed jars are rejected automatically. If induction sealing is required, a foil liner is placed inside the cap. After capping, jars pass under an induction sealer where a high-frequency electromagnetic field heats the foil, bonding it to the jar rim. The seal creates a hermetic barrier that prevents oxygen ingress and oil separation. Labeled jars move to a wraparound or pressure-sensitive labeling station. Labels are applied using servo-controlled applicators, and optical sensors verify alignment and barcode presence. Rejected units are diverted to inspection lanes. Coded printing systems, typically thermal inkjet or laser, apply batch numbers and date codes to the lid or shoulder of each jar. The print system is synchronized with the conveyor speed to ensure clear, consistent marking. Jars are grouped into sets using collation conveyors and loaded into corrugated cartons or shrink-wrap trays. Case packers use robotic arms or mechanical pushers. Sealed cases are labeled with logistic codes and moved to palletizers. Palletizing systems stack cases using programmed layer patterns. Slip sheets are added as needed, and completed pallets are stretch-wrapped with plastic film to stabilize the load for transport. Each pallet receives an RFID tag or barcode label for warehouse tracking. Throughout production, inline sensors monitor critical parameters. These include product temperature, flow rate, fill weight, torque, seal integrity, and label placement. Data is logged by the Central Manufacturing Execution System and linked to batch tracking systems for traceability. Process water used in cleaning and ingredient dissolution is stored separately and heated as needed. All process equipment is connected to CIP systems that circulate detergent and rinse solutions through pipes, tanks, pumps, and valves at scheduled intervals. Cleaning sequences are validated using conductivity, temperature, and flow sensors. Environmental conditions such as air, temperature, humidity, and particulate levels are regulated in processing areas using HVAC systems with HEPA filtration. Maintaining a controlled environment prevents moisture pickup by roasted peanuts and ensures consistent flow behavior of the peanut paste during grinding and filling. Roasting profiles are monitored using thermal sensors and data loggers. Temperature curves are logged and compared against reference curves to ensure even development across peanut batches. Real-time moisture analyzers positioned at the roaster exit verify dehydration targets. Particle size of the final peanut butter is measured using laser diffraction or sieving techniques. Target particle size is typically below 30 microns for smooth varieties and above 100 microns for crunchy variants. Crunchy peanut butter includes the addition of roasted peanut granules, which are prepared separately using coarse grinders, and added post-homogenization under low shear to maintain particle integrity. Oil. Separation resistance is measured during quality control using centrifuge testing or accelerated shelf life studies. Stabilizer effectiveness is confirmed through oil migration testing at elevated temperatures over time. Nutella production begins with the individual preparation of its components: hazelnuts, sugar, cocoa powder, vegetable oil, skimmed milk powder, lecithin, and vanillin. Each raw material is handled separately in dedicated systems to ensure proper particle size, mixing compatibility, and thermal behavior before integration. Hazelnuts are received shelled and pre-cleaned. They are conveyed through pneumatic lines into vibratory feeders that regulate flow into pre-roasting storage silos. From these silos, hazelnuts are metered into a continuous roasting system. Roasting occurs in horizontal convection tunnels or rotating cylindrical chambers, typically at 140 C, 160 degrees C for 20-25 minutes, depending on kernel moisture. The goal is to reach a final moisture level below 2% and to initiate flavor development. Post-roasting, nuts are directed into cooling drums or belt coolers. Forced ambient air lowers kernel temperature to below 30 degrees Celsius before further handling. The next step is blanching, where the brown skin is removed. This is done using mechanical friction rollers or pressurized steam exposure, depending on the desired throughput. Skin is separated by aspiration. The blanched nuts are then split and sorted by size via oscillating sieves, and undersized fragments are diverted. Cleaned, roasted hazelnuts are passed through a primary grinding phase using disc mills or pin mills to produce a coarse meal. This intermediate product is directed into a secondary grinding stage, often a ball mill or high-speed impact mill, which reduces particle size to a fine paste. Typical particle sizes are reduced to under 30 microns at this stage, producing a flowable hazelnut slurry with partial oil release. In parallel, sugar is handled separately. Granulated sugar is milled using air-classifying impact mills to reduce particle size and ensure dissolution in the final product. The resulting fine sugar powder is transferred pneumatically to dosing silos. A similar dry handling system is used for skimmed milk powder, which is fed into mixers via enclosed screw conveyors. Cocoa powder is stored in low humidity silos and transferred through sealed auger systems to prevent moisture absorption. It is typically defatted and pre-sifted to avoid clumps or oversized particles. All powdered ingredients, sugar, milk, and cocoa, are dry blended using horizontal ribbon blenders. These blenders operate at low speed to achieve uniform mixing without generating excess dust. The vegetable oil, primarily refined palm oil, is kept in liquid state in temperature-controlled storage tanks maintained at 45 to 50 degrees C. Oil is pumped through inline filters and metered into mixing systems via flow control valves. The oil acts as the continuous phase for the final emulsion and must be dosed with high consistency. All components are transferred into a batch mixing system, a stainless steel planetary mixer, or a high viscosity processing vessel equipped with anchor agitators. The sequence starts with oil and hazelnut paste, followed by gradual incorporation of the powdered mix. Agitation is applied in stages, with high torque, low speed mixing used for initial wetting and medium speed agitation for full dispersion. Lecithin, added to control emulsion stability and flow, is stored in small heated tanks and introduced last. It is pre-mixed with a portion of the oil phase and dosed via peristaltic or gear pumps. Concentration is typically around 0.3% of the total mass. Vanillin, in synthetic form or as part of a flavoring premix, is injected at low concentrations and blended briefly under vacuum to prevent volatilization. The batch undergoes a refining stage using a 5-roll or 3-roll mill. The paste is pressed through steel rollers, reducing particle agglomerates and improving surface smoothness. The rollers operate at progressively higher speeds to create shear differentials, compressing solids and distributing fat evenly. Target final particle size is below 25 microns. After refining, the product is transferred to a conche, a jacketed horizontal mixer equipped with large mixing blades. The conching phase continues kneading at elevated temperatures of 50-60 degrees Celsius for 1 to 3 hours. This step enhances mouthfeel, disperses volatile compounds, and improves gloss by coating all particles with fat. Upon completion, the paste moves to a vacuum degassing tank where trapped air is removed. Vacuum is applied at 0.8 to 0.9 bar, while slow paddles maintain circulation. This step prevents air pockets in packaging and reduces oxidative degradation. The degassed product is homogenized through a low shear inline mixer to stabilize viscosity. The finished spread is transferred via jacketed pipelines to holding tanks prior to filling. These tanks are fitted with variable speed agitators and are temperature controlled at 40-45 degrees Celsius. A load cell system measures tank contents, coordinating flow to the packaging line. Transfer is performed with sanitary-grade rotary load pumps for accurate low-shear movement of viscous material. In the filling area, jars are supplied via unscramblers and aligned onto conveyors. They pass under vision cameras to confirm shape and cleanliness. Filling is done using servo-controlled piston fillers or mass flow metering systems. Fill nozzles are jacketed and temperature controlled to maintain flow characteristics. Fill volumes are typically accurate to within plus 0.5%. After filling, jars are sealed with aluminum foil using induction sealing. A liner is embedded inside each cap. When the cap is torqued onto the jar and passed under the induction head, an electromagnetic field heats the foil, bonding it to the jar rim. This creates an oxygen barrier and prevents oil migration. Caps are applied using rotary or inline capping machines with torque monitoring. If torque deviates from preset values, jars are rejected. Sealed jars move to the labeling station, where pressure-sensitive or shrink-wrap labels are applied. Labeling heads are adjusted for jar geometry and verified by optical sensors. Next, jars are passed under thermal inkjet printers, which apply date codes and batch identifiers. Printers are aligned with conveyor timing to ensure sharp, legible printing. Codes are verified by barcode readers or OCR systems. Rejected jars are diverted using pneumatic pushers. Labeled jars are grouped into sets using automated collation conveyors. Depending on destination, they may be packed into cardboard cartons or shrink-wrapped into trays. Cartoning machines erect boxes, load jars, and apply closure glue automatically. Case packers then arrange cartons into shipping cases with robotic arms. Shipping cases are sealed using hot melt glue applicators or tape dispensers and labeled with printed logistics data. The labeled cases are scanned, weighed, and conveyed to a palletizing station. Robotic palletizers stack cases according to optimized patterns, using vacuum or mechanical end effectors. Pallets are wrapped using rotary arm stretch wrappers. Film is tensioned to maintain structural integrity without distorting the cartons. Pallets are tagged with scannable barcodes or RFID labels for traceability. Throughout the entire production process, all operations are controlled and logged by a PLC-driven SCADA system. This includes ingredient dosing, thermal profiles, particle size measurements, fill volumes, torque levels, and packaging throughput. Parameters are displayed on HMI terminals and stored in batch records for traceability. Strawberry jam manufacturing begins with bulk delivery of strawberries in refrigerated containers. The fruit arrives pre-sorted or in raw form depending on source. Upon unloading, strawberries are tipped into stainless steel flume tanks where they are submerged in chilled water to reduce field heat and initiate washing. The strawberries are conveyed out of the wash tank using cleated food-grade belt elevators. A high-pressure spray bar located at the discharge point removes surface contaminants. Excess water is removed by air knives or centrifugal dewatering systems. Cleaned fruit is conveyed to the inspection station. At the inspection stage, strawberries pass over a slow-moving belt or roller table equipped with manual or optical sorters. Defective, underripe, or foreign objects are removed. High-resolution cameras with multispectral imaging may be used for automatic defect detection. Rejected items are separated using pneumatic actuators or diverters. Clean, sorted strawberries are directed to the hulling station. Hulling machines use rotating rubber fingers or mechanical plungers to remove the calyx and stem. The removed portions are separated by air aspiration. Hulled fruit is transferred to a temporary buffer hopper before size reduction. The hulling hopper meters strawberries into a dicing or pulping system. Dicing machines use oscillating blades to produce uniform fruit pieces. For homogeneous jam, fruit is passed through a finisher or pulper equipped with perforated screens and rotating paddles to produce a consistent puree. Screen aperture determines the level of texture in the final product. Pulpy fruit mass is weighed using inline load cells or flow meters and directed to a batching tank. In parallel, sugar is conveyed from silos or bulk bags into a dry blending unit. Sugar is sometimes preheated or dissolved in deionized water to create a syrup. This is controlled by mass flow regulation and prepared in jacketed mixing tanks equipped with agitators. Pectin is added either as a powder or as a pre-dispersed liquid. Powdered pectin is mixed with a portion of sugar to prevent clumping during hydration. The blend is fed into the batching tank via screw feeders or high shear dispersers. The type and concentration of pectin depend on the desired gel strength and fruit acidity. Citric acid is introduced to adjust pH, typically to the range of 3.1-3.4, which optimizes pectin gelation. Acid is dosed from a separate tank using peristaltic pumps, monitored by inline pH probes. The exact amount is calculated based on the natural acidity of the strawberry pulp, which is measured per batch. In certain formulations, calcium salts may be added to activate low methoxyl pectins. These are metered in precise amounts using microdosing pumps. Water content is balanced by calculating the moisture level of incoming fruit and adjusting with deionized water or fruit juice concentrates. The full formulation, strawberry mass, sugar, pectin, acid, and optional additives, is transferred to a batch vacuum cooker. The cooking vessel is a steam-jacketed stainless steel kettle, often equipped with an anchor agitator and a central high shear rotor for uniform heat transfer and reduced localized scorching. Cooking parameters are set to evaporate excess moisture, invert part of the sucrose, and activate pectin. The process is performed under partial vacuum to allow boiling at lower temperatures, preserving color and flavor while reducing thermal degradation. Typical target solids content for jam is 65-68 degree bricks, measured with inline refractometers. During cooking, water vapor is extracted through a condenser system connected to the vacuum circuit. Condensate is collected and removed via gravity drains or vacuum traps. The jam mass is circulated continuously through the cooker using sanitary centrifugal pumps. This ensures uniform heating and prevents sedimentation of fruit particles. Once the desired bricks and viscosity are achieved, the batch is cooled through a scraped surface heat exchanger. This unit has a rotor with fixed blades that continuously remove product from the heat transfer surface, enabling rapid cooling while preventing fouling. Product temperature is reduced to below 85 degrees Celsius to prepare for filling. Deaeration is performed inline or in a separate vacuum tank. This step removes entrained air bubbles introduced during cooking and agitation. Vacuum is maintained at approximately 0.8 bar, while slow agitation is applied to stabilize the product's density and texture. Optional flavoring agents or color corrections are added at this stage. Natural strawberry flavors or concentrated fruit essences are introduced through metering systems. Any added color is dispersed into a small portion of jam and blended thoroughly to prevent streaking. The final mixture is homogenized using low shear mixers to avoid foam generation. Finished jam is held in surge tanks equipped with level sensors, slow speed agitators, and thermal jackets to maintain flowability. Surge tanks are connected to the filling system via positive displacement pumps or rotary lobe pumps that handle viscous products with suspended solids. Glass jars or plastic containers are depalletized and transferred to the filling line using timing screws and indexing star wheels. Containers are first rinsed with filtered air or ionized air jets. Jars are checked by vision systems for cleanliness and structural integrity. Jam is filled hot, usually between 80-85 degrees Celsius, to enable vacuum sealing after capping. Filling is performed using piston fillers or mass flow-based servo systems. Fill volume is precisely controlled to match container dimensions and headspace requirements. Foaming is minimized by diving nozzles that dispense product near the base of the container. Immediately after filling, containers pass through a capping station. Metal twist-off caps with vacuum buttons or plastic snap-on lids are applied by mechanical torque heads. For metal closures, steam injection may be used just before capping to displace air and create a vacuum as the container cools. Capped jars move through an inverted holding tunnel or a rotary cooling system. Cooling is carried out using ambient air or chilled water sprays to bring the product below 40 degrees Celsius. Gradual cooling prevents thermal shock to containers and promotes vacuum formation in sealed jars. Vacuum level is verified through cap button testing. Non-vacuum jars are automatically rejected. Labeling follows cooling. Jars are dried using air knives or infrared heaters before entering the labeler. Labels are applied using pressure-sensitive or hot melt glue systems, depending on the label substrate and application speed. Coded information such as production date, expiration, and batch number is printed using thermal inkjet or laser coders. Print location and clarity are verified by high-speed vision systems. Jars failing print quality checks are removed from the line. Labeled jars are grouped into cartons using robotic pick-and-place arms or mechanical collators. Cartons are formed from flat blanks, glued, and sealed using flap folders and glue guns. Carton integrity is checked by sensors measuring weight and dimensions. Cases are packed into shipping boxes or trays. Box formers erect corrugated cases, which are filled and sealed on a continuous motion line. Finished cases are conveyed to an automated palletizer, which stacks them in configured patterns for optimal stability. Pallets are conveyed to a stretch wrapping system where film is applied under tension. Each pallet is labeled with a scannable ID, linked to batch and traceability data. Wrapped pallets are moved to staging zones for distribution or temperature-controlled storage. Throughout the process, Control systems monitor and log all variables. Programmable logic controllers manage dosing, cooking, filling, and packaging operations. Sensors measure temperature, flow, pressure, and viscosity. Human-machine interfaces provide operators with real-time control and alarms. Brix levels are verified at multiple points using digital inline refractometers. pH is measured with inline glass electrode probes. Final jam consistency is evaluated using rotational viscometers or Bostwick consistometers. Water activity meters confirm product stability. Toothpaste production begins with the batching of raw materials into 3 primary categories: abrasives, humectants, and active ingredients. These components are stored in bulk silos, intermediate bulk containers, and stainless steel drums positioned adjacent to the central mixing facility. Ingredient delivery is managed through automated vacuum conveyors, liquid transfer pumps, and weigh-scale monitored feeders. Abrasives are typically calcium carbonate, hydrated silica, or dicalcium phosphate dihydrate. These powders are conveyed through enclosed pipelines and loaded into high-shear mixing vessels fitted with load cells. Particle size of abrasives is controlled within 5 to 15 microns for optimal cleaning performance without excessive enamel wear. The feed rate is calibrated by rotary valve controllers. Humectants, primarily sorbitol solution, glycerin, and propylene glycol, are stored in temperature-controlled, jacketed tanks. These are pumped into the mixer through flow meter regulated dosing lines. The purpose of humectants is to retain moisture, maintain paste consistency, and prevent drying inside the tube. Viscosity and density of each liquid are tracked by inline sensors during transfer. Deionized water is introduced in precise volume based on formulation requirements. The water is pre-treated via reverse osmosis filtration and UV sterilization, then dosed into the batch using mass flow controllers to ensure accurate hydration of solids. Active ingredients such as sodium fluoride or stannous fluoride are pre-blended in secondary mixing tanks before being introduced to the main mixer. These compounds are sensitive to pH and temperature, requiring separate handling. Dosing is performed using positive displacement pumps to achieve concentrations typically around 0.24% for fluoride ion. A surfactant, usually sodium lauryl sulfate, is added last due to its foaming and emulsifying properties. It is introduced in liquid or paste form through heated lines maintained at 30 and 35 degrees Celsius to reduce viscosity. SLS is blended gently to avoid excessive aeration. The target inclusion level ranges between 1.0 to 2.0% depending on the formulation. Hydrocolloid binders such as carboxymethyl cellulose, xanthan gum, or carrageenan are pre-dispersed in warm water before being added to the mixture. These agents control rheology and prevent phase separation. Dispersion tanks use overhead agitators operating at low RPM to avoid clumping. Hydration time is monitored to ensure full polymer expansion before integration. Flavoring oils like spearmint or peppermint are stored in sealed drums and introduced through small volume dosing systems equipped with peristaltic pumps. Flavors are highly concentrated and dosed between 0.3–0.7% by weight. The addition is carried out under vacuum to prevent volatilization. Colorants such as titanium dioxide or FD&C dyes are added as aqueous slurries or pre-dispersed concentrates. These are introduced late in the mix cycle for visual uniformity. Color matching is performed using spectrophotometric sensors positioned above the mixing vessel. Once all materials are loaded, the main batch undergoes high shear mixing. The vessel uses multi-stage impellers, typically a bottom-mounted anchor blade for macro movement and a rotor-stator head for localized dispersion. Mix time ranges from 30 to 45 minutes. Viscosity is continuously measured via in-tank torque sensors and correlated to predefined set points. The entire vessel is held under partial vacuum to remove entrained air. A vacuum pump system pulls air through condensers and liquid traps. Vacuum mixing prevents bubble formation, ensures uniform density, and improves the shelf stability of the final product. Once the batch reaches target viscosity and homogeneity, a recirculation loop begins. The mixture is pumped through inline homogenizers or colloid mills to further reduce particle size and eliminate agglomerates. Homogenization shear rates exceed 10,000 S1, providing a consistent microstructure. The homogenized toothpaste is filtered through stainless steel mesh screens, typically 80 to 120 mesh size, to remove any foreign particles or unblended residue. The product is discharged into vacuum holding tanks equipped with slow-speed agitators to maintain consistency while awaiting packaging. The filling process begins with the transport of toothpaste from holding tanks to the filling line through sanitary diaphragm pumps and flexible hoses. The product is kept under continuous agitation to prevent settling of heavier components. Tubes, either laminate, aluminum, or co-extruded plastic, are loaded into an orienting magazine. Tubes are fed one by one into indexing star wheels that position each unit beneath the filling nozzle. Optical sensors ensure correct alignment based on pre-printed registration marks. Filling nozzles are submerged slightly into each tube and retract upward during discharge to prevent air pockets. Volumetric filling pumps dispense the product in quantities typically ranging from 75 ml to 150 ml. Fill weight is controlled to plus 1% using servo-driven piston pumps or mass flow metering systems. Immediately after filling, the tube passes to the sealing station. For laminate or plastic tubes, the tail is heat sealed using conduction or impulse sealers. The sealing bars clamp the tube end, applying pressure and heat to fuse the inner layers. For aluminum tubes, the tail is folded and crimped mechanically by a multi-head crimping tool. A batch code and timestamp are embossed or inkjet printed onto the sealed end. This information includes production line, time, and lot number for traceability. The print heads are aligned with the tube transport belt and are capable of printing at over 300 units per minute. Filled tubes are ejected onto a conveyor and enter a carton loading station. Flat-folded cartons are erected using vacuum grippers and mechanical pushers, then held open under guide rails. Each tube is inserted automatically, and informational leaflets are added if required by formulation. Cartons are closed using hot melt glue applicators or tuck-in flaps depending on design. Sensors verify the presence of a tube inside each carton. Incomplete units are automatically rejected through diverter arms. Cartons are grouped into shipping cases via a robotic case packer. Cases are assembled from flat blanks, filled, and sealed using hot glue or tape. Case labels are printed and applied using print and apply applicators with real-time data from the production control system. Completed cases are moved onto a palletizer conveyor. An articulated arm robot stacks cases onto pallets in a predefined pattern. Slip sheets are inserted automatically between layers to maintain stability. Full pallets are stretch wrapped using rotating ring or arm wrappers. The film tension and overlap are adjustable to prevent compression of cartons while ensuring unit load integrity. Pallets are labeled on two sides with shipping and tracking information. Barcode scanners verify label accuracy and update inventory systems. Pallets are then transferred to staging zones for warehousing or direct shipment. During production, the entire process is governed by a centralized control system. Each piece of equipment is connected through a SCADA network, allowing operators to monitor tank levels, batch status, mix parameters, and fill rates from an HMI panel. Ingredient weighing stations utilize barcode scanners and recipe control software to prevent cross-contamination and ensure formula compliance. Any deviation from programmed weight tolerances triggers an alarm and locks further processing. Rheological properties are tested in real time using rotational viscometers. Samples from each batch are drawn via sampling ports and analyzed for yield stress, viscosity at shear, and thixotropy to confirm product performance. pH levels are measured with inline electrodes during mixing, typically targeting a range of 6.5 to 7.5, depending on the actives used. Fluoride ion concentration is verified using ion-selective electrodes to confirm dosing accuracy. Toothpaste density is measured using vibrating tube densitometers and compared against target values to ensure proper tube filling weight. Deviations are corrected by adjusting water content or mixing parameters. Color uniformity is monitored using inline spectrophotometers calibrated to CIE lab. Color space standards. Any deviation beyond preset delta E values prompts batch correction or rejection. Each major tank and mixer is equipped with CIP systems consisting of rotating spray balls, detergent feed lines, and automated rinse cycles. CIP cycles are logged in the MES to maintain batch integrity. Final packaging lines are equipped with vision systems to detect carton defects, misalignment, or barcode errors. These systems use high-resolution cameras and rejection logic to divert non-conforming packages. High-speed toothpaste production lines are capable of producing over 300 tubes per minute, with batch sizes ranging from 1,000 to 6,000 liters depending on demand. Formulation changes are executed by software-driven recipe management with automated valve sequencing and ingredient routing. Mouthwash production begins with the preparation of purified water, which serves as the base solvent for all ingredients. The water undergoes reverse osmosis, filtration, followed by ultraviolet sterilization. Conductivity meters and microbial sensors ensure that the water meets pharmaceutical grade specifications before being stored in stainless steel holding tanks equipped with continuous recirculation systems to prevent stagnation. Batch production starts with loading water into a stainless steel jacketed mixing vessel fitted with high shear agitators. The vessel is mounted on load cells to allow for precise weight-based dosing of each component. All ingredients are added in a controlled sequence based on formulation parameters pre-programmed into the batch control system. Humectants are added first. Glycerin, sorbitol solution, or propylene glycol is pumped from storage tanks using metered diaphragm pumps. Flow meters and temperature sensors track each transfer. These compounds help retain moisture and provide viscosity and sweetness. Typical inclusion ranges from 5 to 25% by weight. Alcohol, when used as a solvent and preservative, is added next. Ethanol is transferred from explosion-proof storage tanks through stainless steel piping. The addition is performed under closed-loop nitrogen-blanketed conditions to minimize evaporation. Flow rate is monitored by mass flow meters, and volume is logged digitally for each batch. Final ethanol concentration typically ranges from 15 to 27% in alcohol-based formulations. Active ingredients are added once the base solution stabilizes. These include antimicrobial agents such as cetylpyridinium chloride, chlorhexidine gluconate, or essential oil blends. Active ingredient dosing is highly precise and performed using peristaltic pumps from sealed ingredient totes. Target concentration is verified using inline UV absorbance detectors or conductivity probes depending on the compound. Fluoride compounds, such as sodium fluoride or stannous fluoride, are prepared as pre-dissolved concentrates in separate mixing tanks using deionized water. These are dosed into the main batch at levels typically ranging from 225 to 1000 ppm fluoride ion. Addition is done slowly to avoid precipitation, and pH is adjusted immediately. Afterward, to maintain stability. Flavoring agents are next. These include mint oils, cinnamon, or eucalyptus derivatives. Essential oils are highly volatile and introduced using closed-loop pumps with nitrogen pressurization. Solubility is aided by pre-mixing oils with non-ionic surfactants or alcohol carriers before addition. Colorants are added in the form of water-soluble dye solutions or color dispersions. Each colorant is pre-weighed and diluted before dosing. Magnetic stirrers or inline static mixers ensure uniform dispersion. Optical sensors may be mounted over the mixing tank to confirm target lab or chassis color values in real time. Preservatives such as methylparaben, propylparaben, or sodium benzoate are added next. These are introduced as aqueous solutions prepared in separate blend tanks. Preservative concentration ranges from 0.05–0.2% depending on product shelf life requirements and microbial load assessments. Addition is carried out under agitation to ensure full dissolution. Sweeteners such as sodium saccharin, xylitol, or sucralose are added to enhance palatability. These are dosed in small concentrations, typically below 0.5%, using high-precision auger feeders or micro-piston pumps depending on the form. Mixing continues at low speed to prevent foaming. The final mouthwash formulation is adjusted for pH. Aqueous solutions of sodium hydroxide or citric acid are prepared in auxiliary tanks and dosed using digital peristaltic pumps. pH is continuously monitored by inline probes to maintain a range typically between 4.5 and 7.0, depending on the active ingredients and flavor profile. Anti-foaming agents are optionally added during the final mixing phase. These include dimethicone emulsions or food-grade silicone oils. Addition is controlled via gear pumps and only applied when foaming exceeds threshold levels, as detected by capacitive foam sensors inside the vessel. After full ingredient incorporation, the batch is subjected to a recirculation loop using a centrifugal pump system. The liquid is passed through an inline homogenizer or static mixer to eliminate stratification and achieve consistent texture and solute distribution. The blended product is filtered through sanitary-grade filtration systems, typically consisting of 5 to 10 micron nominal filters, followed by 0.45 micron absolute membrane filters. Filters are housed in stainless steel vessels with differential pressure gauges to monitor clogging. Filtration removes undissolved solids and potential contaminants prior to packaging. Filtered mouthwash is then transferred via sanitary pipelines to intermediate storage tanks or directly to the filling line. Holding tanks are jacketed and equipped with low shear agitators to maintain homogeneity. Each tank includes a vented filter to preserve sterility and pressure balance. Bottling begins with automatic bottle unscramblers that orient and feed empty bottles onto the production conveyor. Bottles are conveyed under a rinsing station where filtered air or ozonated water is sprayed into each bottle via nozzle inserts. Rinse nozzles retract after each cycle, and residual rinse is removed using vacuum-assisted drainage. Clean bottles move to the filling carousel. Volumetric or flow meter-based filling systems dispense liquid into each bottle. Nozzles are equipped with anti-drip valves and may dive into the bottleneck to minimize turbulence. Fill volumes are controlled to within +1 ml using servo-controlled pistons or mass flow controllers. Line speeds may exceed 200 bottles per minute depending on bottle size and product viscosity. Filled bottles proceed to the capping station. Caps are sorted via a centrifugal feeder or vibratory bowl and oriented into a chute. A pick-and-place system applies each cap to a bottle, and servo torque heads tighten the cap to precise specifications. Torque monitoring systems verify seal integrity for each unit. Induction foil sealing may be used, especially for alcohol-based or high-value formulas. Bottles pass under an induction coil, which heats the foil liner inside the cap. The foil bonds to the bottle, rim through localized heat and pressure, creating a tamper-evident, leak-proof seal. Labeled bottles proceed through a pressure-sensitive labeling station. Label spools feed through optical sensors and tensioning arms. Each label is applied to the bottle using rubber rollers or air jets and wrapped around the circumference. Vision systems verify label placement, orientation, and print quality. Optional shrink bands are applied for tamper evidence. Bands are dropped onto the bottlenecks and conveyed through a shrink tunnel heated by steam or infrared elements. Temperature control ensures uniform band shrinkage without damaging the label. Coded printing is applied next. Thermal inkjet or laser printers mark each bottle with batch number, timestamp, and expiration date. Printers are mounted on adjustable arms and synchronized with the conveyor motion to maintain legibility at high speeds. Bottles are collected into groups using pack-off tables or automated grouping conveyors. Depending on the packaging format, grouped bottles are transferred to a cartoner or case packer. Cartons are erected automatically, and bottles are inserted using push arms or robotic arms. Cases are formed using automatic case erectors. Cartons are loaded into corrugated shipping cases in a pre-programmed layout. Flaps are closed using hot melt glue or tape, and cases are labeled with shipping information using print and apply labelers. Completed cases are transported to palletizing systems. Robotic palletizers stack cases layer by layer using vacuum grippers or mechanical forks. Slip sheets are inserted as needed. Stack configurations follow warehouse layout and transport requirements. Each pallet is stretch wrapped using rotary arm or turntable systems. Stretch film is applied with controlled tension and overlap to stabilize the load. Barcode labels are applied to two adjacent sides for warehouse scanning. Throughout the entire production process, data is logged by a centralized manufacturing execution system. Ingredient usage, batch ID, tank temperatures, pH levels, fill weights, and cap torques are recorded in real time. Deviations outside of tolerance trigger automatic alarms and halt affected processes. Inline process analytical technologies are used for real-time monitoring of active concentration, color consistency, and microbial integrity. Ultraviolet spectrophotometers, or Raman probes, measure concentrations of key actives like fluoride or chlorhexidine without requiring sample removal. Inventory management systems track lot numbers of all raw materials and link them to finished product batches for traceability. Each component is barcoded and scanned before addition to a batch, ensuring compliance with formulation requirements. Shampoo production begins with the preparation of process, water, which functions as the primary carrier for all ingredients. Incoming water is treated through multi-stage filtration systems that include sand filtration, activated carbon beds, reverse osmosis membranes, and ultraviolet sterilization. Treated water is stored in stainless steel buffer tanks equipped with recirculation pumps to maintain uniform temperature and prevent stratification. The manufacturing process is typically batch-based, although some high-volume lines use semi-continuous systems. Each batch starts with charging a jacketed stainless steel mixing vessel with a calculated volume of purified water. The vessel is mounted on load cells that provide real-time mass data to the batch control system. Agitation begins immediately using a slow-speed anchor impeller to establish bulk circulation. Primary surfactants are added first. These are the main cleansing agents and usually include sodium laureth sulfate, sodium lauryl sulfate, ammonium laureth sulfate, or sodium cocoyl isethionate, depending on formulation. Liquid surfactants are pumped from storage tanks using variable speed, centrifugal, or positive displacement pumps. Flow is regulated by mass flow meters, and addition rates are synchronized with agitator speed to avoid excessive foaming. For formulations using solid or paste surfactants, the materials are pre-dissolved in auxiliary tanks. These tanks are heated via steam or hot water jackets to reduce viscosity and accelerate dissolution. High shear mixers are used to break down surfactant agglomerates before the solution is transferred into the main batch vessel. Once the primary surfactants are fully dispersed, secondary surfactants are introduced. These include cocamidopropyl betaine, sodium cocoamphoacetate, or other amphoteric surfactants that improve mildness and foam stability. These materials are dosed through metered pumps and blended under moderate agitation to ensure compatibility with the primary surfactant system. Thickeners are added next to control viscosity. Depending on the formulation, these may include sodium chloride, ammonium chloride, hydroxyethyl cellulose, xanthan gum, or acrylate-based polymers. Salt-based thickeners are dissolved directly into the batch using controlled dosing, while polymeric thickeners are prehydrated in separate dispersion tanks to prevent lump formation. Polymer dispersions are slowly added under high shear conditions to ensure uniform distribution. Conditioning agents are incorporated after viscosity begins to develop. These include cationic polymers, such as polyquaternium compounds, guar hydroxypropyl trimonium chloride, or silicone emulsions. Silicone conditioning agents, such as dimethicone or amidimethicone, are supplied as stable emulsions and added under low shear agitation to prevent emulsion breakage. The batch temperature is carefully controlled, typically between 30-45 degrees C, to maintain emulsion stability. Pearlizing agents are added when a pearlescent appearance is required. These materials often consist of ethylene glycol, distearate, or glycol monostearate dispersions. Pearlizing agents are melted in heated side vessels and added to the batch at elevated temperature. Controlled cooling is then used to crystallize the pearlescent particles, producing uniform light-reflecting platelets throughout the shampoo. Chelating agents such as disodium EDTA are introduced to bind metal ions present in water or raw materials. These are added early in the process, usually dissolved in water, to improve product stability and preservative effectiveness. Dosing is managed using precision pumps due to the low concentration required. Preservatives are added once the surfactant system is fully established. These may include phenoxyethanol, sodium benzoate, potassium sorbate, or blended preservative systems. Preservatives are typically added as liquid concentrates and dispersed thoroughly under continuous agitation. The concentration is controlled to achieve microbial stability without affecting product performance. pH adjustment follows. Shampoo formulations generally target a pH range between 4.5 and 6.5 to align with hair and scalp compatibility. pH adjusters, such as citric acid or sodium hydroxide, are prepared as dilute solutions in auxiliary tanks. These solutions are dosed gradually, while pH is monitored using inline probes connected to the batch control system. Adjustments are made incrementally to avoid overshooting target values. Fragrance is added near the end of the mixing process. Fragrance oils are complex blends of aromatic compounds and are typically pre-dissolved in a solubilizer or surfactant base before addition. This prevents separation or clouding. Fragrance addition is carried out under low agitation to minimize volatilization and foaming. Dosing is controlled with high accuracy peristaltic pumps due to the low inclusion rate. Colorants are added as diluted solutions or dispersions. Liquid dyes are metered into the batch, while powdered pigments are pre-dispersed in water or surfactant solution to ensure uniform color distribution. Optical sensors or laboratory sampling is used to confirm color consistency against formulation standards. Once all ingredients are added, the batch undergoes a final homogenization phase. The shampoo is circulated through an inline rotastator mixer or colloid mill to eliminate micro lumps, improve clarity, and ensure uniform viscosity. Shear rates are carefully controlled to avoid degrading polymer thickeners or breaking silicone emulsions. During homogenization, air entrainment is minimized. Some systems apply vacuum to the mixing vessel to remove entrapped air bubbles. Vacuum levels are controlled to prevent excessive evaporation of volatile components such as fragrance. After homogenization, the shampoo is transferred to a finishing tank. This tank is equipped with gentle agitation to maintain homogeneity while allowing the product to cool to filling temperature. Cooling is achieved via the vessel jacket using chilled water or ambient cooling loops. Final viscosity develops during this cooling phase, particularly for salt or polymer thickened systems. Quality parameters are verified at this stage. Viscosity is measured using rotational viscometers, density is checked using digital densitometers, and pH is reconfirmed. Adjustments can still be made by adding small amounts of water, thickener, or pH modifier if required. The finished shampoo is then pumped through sanitary pipelines to the filling area. Transfer pumps are selected based on product viscosity and shear sensitivity, commonly using lobe pumps or progressive cavity pumps. Flow rates are synchronized with filling line demand to maintain steady supply. Packaging begins with bottle preparation. Empty bottles made from PET, HDPE, or PP are delivered to the line in bulk and fed into an unscrambler. The unscrambler orients bottles upright and transfers them onto a conveyor system. Bottles pass through an air rinsing station where filtered air removes dust or debris from the interior. Bottles are conveyed to the filling machine. Filling systems may be volumetric piston fillers, mass flow fillers, or time pressure fillers, depending on product viscosity and accuracy requirements. Filling nozzles descend into the bottleneck to reduce splashing and foaming. Fill volumes are controlled to tight tolerances, typically within plus 0.5%. Filled bottles move to the capping station. Caps are sorted and oriented using vibratory bowl feeders. Each cap is placed onto a bottle and tightened using torque-controlled capping heads. Torque values are monitored continuously to ensure consistent closure without deforming the bottle or cap threads. If induction sealing is used, bottles pass under an induction coil that heats a foil liner inside the cap. The liner bonds to the bottle rim, creating a hermetic seal. Coil power and conveyor speed are calibrated to ensure uniform sealing without overheating the product. Labeled bottles proceed to the labeling station. Labels may be pressure sensitive, shrink sleeve, or wraparound types. Pressure sensitive labels are applied using rollers and air jets, with registration controlled by optical sensors. Shrink sleeves are applied loosely and then passed through a heat tunnel where they conform tightly to the bottle shape. Batch codes and expiration dates are printed on the bottle or label using inkjet or laser coding systems. Print quality is verified by vision systems that detect missing or illegible codes and trigger rejection mechanisms. Bottles are then grouped for secondary packaging. Automatic packers collate bottles into predefined counts and load them into cartons or trays. Cartons are erected from flat blanks and sealed using hot melt adhesive. Case packers arrange cartons into shipping cases according to palletization requirements. Shipping cases are conveyed to palletizing systems. Robotic palletizers stack cases onto pallets in programmed patterns to maximize stability and space utilization. Slip sheets may be inserted between layers. Completed pallets are wrapped with stretch film to secure the load. Throughout the entire process, production is controlled by a centralized automation system. Programmable logic controllers manage ingredient dosing, mixing speeds, temperatures, and transfer operations. A supervisory control and data acquisition system provides real-time monitoring, data logging, and batch traceability. Recipe management software stores detailed formulation parameters, allowing rapid changeover between different shampoo variants such as moisturizing, clarifying, volumizing, or color protecting types. Automated valve manifolds route ingredients to the correct vessels based on the selected recipe. Raw material inventory is tracked digitally. Each ingredient lot is scanned and logged before use, and consumption data is automatically reconciled with production output. This ensures accurate material planning and batch traceability. Cleaning cycles between batches are executed using automated clean-in-place systems. These systems circulate cleaning solutions and rinse water through vessels, pipes, pumps, and fillers without disassembly. Cleaning parameters such as time, temperature, and flow rate are recorded for each cycle. Tim Hortons donut production begins with a dry mix formulation containing enriched wheat flour, sugar, dextrose, non-fat dry milk, salt, leavening agents like sodium acid pyrophosphate and baking soda, and dough conditioners. These dry ingredients are stored in silos or large bagged quantities and conveyed into industrial mixers via auger-fed hoppers. Water, maintained at a controlled temperature between 26-30 degrees C, is added automatically by volume through solenoid-controlled valves. The mixture undergoes a high-capacity mixing process using horizontal paddle mixers that operate for approximately 10 to 12 minutes until a smooth, elastic dough forms. Dough temperature is precisely maintained to ensure consistent gluten development. The mixed dough is transferred to a resting conveyor where it undergoes a short fermentation stage, typically lasting 10 to 15 minutes. During this period, gluten strands relax, allowing easier downstream sheeting and cutting. The dough enters a sheeting system composed of heavy-duty rollers that gradually flatten the dough to a uniform thickness, often between 8 to 12 millimeters depending on the donut type. A dusting system coats the sheet with a thin layer of flour or starch to prevent sticking. Next, rotary cutters mounted on a continuous belt use oscillating blades and die shapes to stamp out ring donuts, filled donut bases, and specialty shapes. Hole cutouts are collected via vacuum suction and reintroduced into the dough stream to reduce waste. The shaped pieces drop onto a mesh conveyor belt, which transfers them into a proofing chamber. The proofer is a humidity and temperature-controlled enclosure typically maintained at 38-42 degrees and 75-85% relative humidity. Here, yeast-leavened donuts undergo final fermentation for 35 to 50 minutes, doubling in size. Upon exiting the proofer, donuts enter a continuous fryer via an infeed belt that gently lowers each piece into the oil. The fryer is filled with high-stability vegetable shortening, held at a consistent temperature of 185-190 degrees C. Conveyor arms with paddles submerge the donuts briefly before flipping mechanisms rotate them halfway through the cycle to ensure even cooking on both sides. Each donut spends 90-120 seconds in the fryer. Oil filtration systems continuously circulate and clean the oil through mechanical filters and carbon filtration media to maintain clarity and extend oil life. Excess oil is removed from the surface by air knives as donuts exit the fryer. Fried donuts transfer to a cooling conveyor, where forced ambient air reduces product temperature before glazing or filling. For ring donuts, a waterfall-style glazing system coats the tops with sugar glaze. The glazing machine contains a recirculating pump that delivers a steady curtain of glaze to ensure uniform coverage. Filled varieties proceed to an injection station. A synchronized multi-nozzle injector aligns with each donut and dispenses a precise volume of filling, such as fruit jam, Bavarian cream, or chocolate, into the center of the pastry using piston-driven pumps. Fill volumes are regulated down to the gram for product consistency. Specialty donuts requiring additional coatings, such as powdered sugar or cinnamon sugar, enter a rotating tumbler. The tumbler's perforated drum allows excess sugar to fall through while evenly applying the coating as the donuts rotate inside. Sensors monitor rotation speed and coating application rate. For chocolate or icing-topped varieties, donuts pass through a curtain enrobing system or a top-down depositor. The enrobing system consists of a tempering kettle and a heated pump that maintains the chocolate or icing at its working viscosity, typically around 40-45 degrees Celsius. Topping depth is controlled by belt speed and curtain thickness. Donuts requiring sprinkles or toppings are conveyed beneath a waterfall depositor or rotary sprinkler. The toppings are dispensed from a vibrating hopper that ensures even spread. Static charge may be applied in some systems to increase topping adhesion to the wet icing. Once decorated or filled, donuts proceed through a spiral cooling tower. The spiral conveyor allows a compact vertical footprint while offering extended cooling time, typically 15 to 20 minutes. Forced air circulation removes residual heat, allowing products to stabilize before packaging. Each donut then moves through a vision-based quality control system. High-speed cameras scan for defects in size, color, fill placement, or topping consistency. Items outside. Tolerants are rejected automatically using pneumatic pushers. Qualified donuts are then grouped by variety and type using a servo-controlled collation system. Products are aligned into lanes and counted by photoelectric sensors, preparing them for packaging. Packaging is handled by an automated tray loading system. Flat-folded paperboard trays are erected using mechanical arms, and donuts are placed inside via pick-and-place robots with suction grippers. For assorted packs, robotic arms select donuts by type from buffer conveyors. Trays proceed to a lid applicator station, where pre-folded lids are pressed and sealed using glue jets or heat-sensitive adhesives. For retail cases, sealed trays are grouped and shrink-wrapped using polyolefin film, which is cut, wrapped, and heat-shrunk in a tunnel oven operating at around 160 degrees Celsius. Each finished pack receives an inkjet-printed date code and batch number from a variable data printer. The printer adjusts to the motion of the conveyor, ensuring clear marking without interrupting product flow. Packaged products are conveyed to palletizing stations. Robotic palletizers equipped with vacuum or mechanical grippers stack trays in precise layer patterns onto standard pallets. Slip sheets may be inserted between layers for stability. Full pallets are wrapped using a rotary arm stretch wrapper. The film roll is tensioned to apply a tight wrap without deforming the boxes. Wrapped pallets are transferred to refrigerated holding or shipping docks for distribution. Throughout the process, programmable logic controllers synchronize machine timing, belt speeds, pump volumes, and thermal settings. Human-machine interface panels monitor all parameters and log production data. The entire line is modular and scalable, allowing simultaneous production of multiple donut types. Conveyors interlink each station, minimizing manual transfer and optimizing flow. Changes in donut type or size are handled through automated tool change systems or quick swap components. Pre-programmed recipes stored in the central control system reconfigure the line settings within minutes. Staging silos and ingredient feeders are equipped with load cells to precisely meter dry ingredients. Liquid ingredients are stored in jacketed stainless steel tanks with inline agitators to prevent settling or stratification. The dry and liquid ingredient streams merge at the mixer's inlet via butterfly valves controlled by digital weigh scales. The dosing accuracy ensures batch-to-batch uniformity, critical for dough performance during proofing and frying. Proofing chambers are equipped with belt elevation systems that loop the dough pieces through multiple horizontal levels. Fans and humidifiers ensure even air distribution, and digital probes record temperature and humidity in real time. Fryers are segmented into temperature zones with independent heating coils managed by thermocouple feedback. This zoning ensures even coloring across all donut types, regardless of fill or topping. Oil levels are maintained by float-based control valves, and inline filtration runs continuously. Spent oil is periodically replaced using external storage tanks connected by insulated pipelines and pneumatic pumps. The icing station includes a recirculation tank and a filtration mesh that removes solid particles from reused icing. viscosity is measured using a rotational viscometer integrated into the circulation loop. Decorative elements, such as drizzle patterns or text, are applied using programmable depositor heads, which trace patterns based on CAD instructions and synchronize with conveyor speed to ensure alignment. Filled donuts pass through an X-ray inspection tunnel, identifying underfilled or foreign material contaminated units. Rejected items are diverted to a side conveyor for manual review. Donuts for seasonal assortments are coded with quick response QR markers beneath their trays, allowing downstream distribution centers to sort mixed lots via machine vision systems and RFID tracking. Dunkin' Donuts. Donut production begins with dry ingredient blending, high-protein wheat flour, dextrose, sugar, soy flour, non-fat milk powder, salt, dough conditioners, and chemical leavening agents such as sodium bicarbonate and monocalcium phosphate are measured by weight and transferred into large-capacity industrial mixers using pneumatic conveying systems or gravity-fed hoppers. Liquid ingredients, including water, liquid shortening, and egg yolk solids, are preheated and pumped into the mixer via metered dosing systems. Water temperature is held between 27 to 30 degrees Celsius to activate gluten formation without overheating. Mixers equipped with high-torque planetary paddles operate in timed cycles to combine the dough, typically lasting 8 to 12 minutes. Dough temperature is monitored continuously with inline probes. Target final dough temperature is around 27 degrees Celsius for yeast-raised donuts to ensure optimal proofing behavior. Once mixed, the dough is transferred to a resting trough conveyor for gluten relaxation and hydration equilibrium, allowing for consistent sheeting performance. The rested dough moves to a multi-stage sheeting system composed of compression rollers that gradually reduce thickness in incremental stages. Roller gap adjustments are motorized and recipe controlled. Final sheet thickness is typically 9-11 mm, depending on the donut style. A light dusting system applies fine cornstarch or rice flour across the dough sheet surface to prevent sticking. The sheet then feeds into a rotary die cutter system. The cutter contains interchangeable dies for different donut varieties, including ring shapes, filled rounds, bars, and novelty shapes. The cutting drum rotates in synchronization with the conveyor to ensure clean, high-speed cuts. Cut donuts are transferred onto wire mesh proofing trays by vacuum-assisted pick-and-place systems. The trays are automatically stacked into a multi-tiered conveyor rack that moves through a temperature and humidity-controlled proofing chamber. Proofing conditions are held at 38 to 40 degrees Celsius, with 80-85% relative humidity for 35 and 45 minutes. Within the proofer, dough pieces rise and expand due to yeast activity. Conveyor motion is timed so that each tray spends the same duration in the chamber. Sensors track fermentation progression using size and weight benchmarks. After proofing, trays enter an automated unloading system that transfers the dough pieces onto a fryer in-feed belt. Frying oil is a refined, high-stability vegetable shortening maintained at 185-190 degrees C. The fryer contains a dual-zone heating configuration and a submersion system using paddle arms that guide and flip the donuts midway through frying. Total fry time is approximately 90 seconds. Ring donuts are flipped automatically after 45 seconds by rotating bars. Filled donut bases remain face up to maintain a flat bottom. Oil turnover is managed through continuous filtration using a centrifugal separation system and micron-level mechanical filters to remove particulates. As the donuts exit the fryer, excess oil is removed by angled mesh belts and compressed air nozzles. Products then travel along a cooling conveyor system with ambient airflow, reducing surface temperature below 35 degrees Celsius before handling. Ring donuts destined for glazing pass under a waterfall-style glazing station. The glazing tank contains a high shear mixer that maintains solution homogeneity. A recirculating pump delivers glaze to a curtain nozzle that flows over the donuts. Excess glaze drains back into the holding tank through a mesh screen. Filled donuts proceed to a pressurized injection system. Each donut aligns with a dual or quad nozzle filler head that penetrates the side or bottom. Piston pumps dispense fillings such as jelly, cream, or custard with precision-controlled volume, typically 18 to 25 grams per unit. After filling, donuts requiring icing are transferred to a top-down depositor. This system uses heated reservoirs that keep icings at 40 to 45 degrees Celsius. Servo-controlled valves open and close based on donut presence detected by photoelectric sensors. Depositor heads apply a measured layer of icing across the top surface. For varieties requiring toppings, donuts travel under a vibratory topping applicator. Toppings such as chopped peanuts, sprinkles, or coconut shavings are dispensed via a rotating auger or oscillating tray, which evenly distributes material across the icing surface. Adhesion is achieved by timing the topping deposit immediately after icing application. Powder-coated or sugar-rolled donuts are conveyed into a rotating tumbler drum. A controlled feed of granulated or powdered sugar enters through a dosing hopper. The drum rotates at a calibrated RPM to coat donuts uniformly without damaging their structure. Fine mesh filters remove sugar clumps from the recirculation stream. Donuts with drizzle designs undergo a separate decoration process using linear motion gantry arms. These arms carry nozzles that deposit thin lines of icing, chocolate, or flavored syrup in programmed patterns. Motion control algorithms synchronize nozzle movement with conveyor speed for accurate designs. Post-decoration, all donuts pass through a spiral cooling tower. This vertically stacked conveyor system allows compact, high-capacity cooling with continuous airflow. Residence time is typically 15 to 20 minutes, allowing toppings to set and fillings to stabilize. Donuts exit the spiral cooler and enter a high-speed vision inspection system. Industrial cameras mounted above and to the side scan each product. Parameters such as size, color, symmetry, icing coverage, and fill injection marks are analyzed in real time. Out-of-spec items are removed via air-jet ejection systems. Acceptable donuts are organized into lanes using servo-driven diverter arms. Grouping is based on variety and pack size. Collation belts accumulate donuts into patterns that match tray cavities. Packaging begins with automatic tray erecting. Flat paperboard blanks are fed into a forming unit that applies glue and folds trays into shape. Form trays move beneath pick-and-place units with vacuum suction cups that deposit donuts into each cavity. Assorted variety packs are assembled by robotic gantries with product recognition software. These systems pull donuts from buffer conveyors and place them according to pre-programmed variety maps. Tray sealing depends on the product format. Some are closed with plastic lids, applied and snapped into place by mechanical presses. Others use film sealing units with heated jaws that apply plastic film over the tray and bond it along the edges. Packaged trays are labeled using thermal inkjet printers. Labels include production codes, variety, and timing information. Alignment sensors ensure accurate label placement without interrupting conveyor flow. Trays are loaded into cardboard master cases using side loading systems. Collapsible cases are automatically erected from flat blanks and fed into the loading station. Case flaps are glued and sealed using hot melt adhesive heads. Filled master cases are conveyed to a robotic palletizer. A vision-guided robot stacks cases in alternating patterns for load stability. Slip sheets are added at programmed intervals to separate layers. The stack height is optimized for transport requirements. Each completed pallet is wrapped with stretch film using a rotary arm wrapper. The arm spins around the stationary pallet, tensioning the film for secure transport. Film overlap and wrap count are controlled digitally to match load size. Wrapped pallets are labeled with barcoded identification tags applied by robotic labelers. Pallets then enter a gravity-fed conveyor line toward refrigerated loading docks or cold storage. Throughout the production line, operations are governed by a distributed control system. Programmable logic controllers handle station-level automation, while supervisory control and data acquisition systems log all machine parameters, production metrics, and alarms. Recipe management software controls all batch-dependent variables, including mixing time, proofing duration, fryer temperature, fill weights, and topping dosages. Each donut type has a profile stored in the system, allowing for rapid product changeovers with minimal downtime. Dry ingredient silos are equipped with level sensors and load cells. Refilling is coordinated with automated delivery systems to ensure continuous availability. Ingredient dosing systems operate under gravimetric and volumetric control for precise formulation. Liquid shortening is held in insulated tanks with inline heaters and agitators to maintain uniform viscosity. Delivery lines are jacketed and circulate hot water to prevent solidification. Pumps use variable frequency drives to adjust flow rate based on batch requirements. Filling hoppers for creams and jellies are jacketed for temperature control and agitated to prevent phase separation. Fill viscosities are monitored using inline viscometers, and pressure is regulated to prevent overfill or underfill. Proofing conveyor belts are made from non-stick, food-grade materials and guided on multiple horizontal tiers. Air circulation is forced through dampers to ensure uniform proofing across all trays. Temperature and humidity are logged for each cycle. Fryer systems include zoned heating elements and oil curtain barriers to minimize heat loss. Oil flow rate and turnover frequency are tracked by volumetric flow meters and recirculation pumps. Air knives at the fryer exit are powered by centrifugal blowers with adjustable nozzles. Their position and pressure are calibrated to strip excess oil without disturbing surface structure or toppings. Glazing tanks are cleaned and refilled on a timed schedule using CIP circuits. Glaze viscosity is maintained with real-time temperature feedback loops and monitored by rotational viscometers. All conveyors, transfer points, and topping stations are modular and mounted on quick-release brackets, allowing reconfiguration for new product lines or seasonal variations. The manufacturing process for Chips Ahoy. Cookies begins with precise dry ingredient batching. Key components include enriched wheat flour, sugar, brown sugar, baking soda, salt, and emulsifiers. These dry ingredients are stored in silos or super sacks and automatically dispensed via auger-fed feeders into high-capacity weigh hoppers. Load cells measure each ingredient to exact tolerances before being discharged into the mixing system. In parallel, liquid ingredients are prepared. These include water, high fructose corn syrup, molasses, glycerin, and vanilla flavoring. Liquid fats, such as palm or soybean oil, are stored in heated, jacketed tanks and pumped through insulated lines to maintain target viscosity. Liquid dosing is controlled using flow meters and metered pumps integrated into the batch control system. All ingredients are conveyed to an automated horizontal batch mixer. The mixing cycle follows a strict sequence: creaming of fats and sugars first, followed by the introduction of liquid components, then gradual incorporation of dry flour-based ingredients. Mixing speed and time are controlled by PLCs based on the dough formulation. Dough temperature is maintained between 20 octa-T4 to preserve texture consistency. Once the base dough is formed, chocolate chips are added. These are stored in climate-controlled hoppers to prevent melting or clumping and are added during the final low-speed mixing phase to avoid breakage. Chip loading is calibrated by weight to ensure uniform distribution across the batch. Mixed dough is discharged from the horizontal mixer into a dough handling system, which typically includes a feed conveyor and a rotary chunker. The chunker breaks large volumes into manageable portions for downstream processing. Dough portions are conveyed to the forming line. Portioned dough enters an extrusion-based depositor system. The depositor uses servo-controlled pistons to extrude dough through circular nozzles onto a moving oven band. Each cookie unit is dropped at exact intervals to maintain spacing and size. Depositor nozzles are non-stick coated and fitted with sensors to detect flow irregularities. The formed dough pieces move directly into a multi-zone continuous baking oven. The oven band is typically a steel mesh or solid band, depending on desired bottom texture. The oven is divided into several independently controlled thermal zones, with temperatures ranging from 180 degrees C to 230 degrees C. Baking duration is precisely set, typically between 6 to 10 minutes. As cookies move through the oven, moisture evaporates rapidly in the early zones, setting the outer structure. Later zones apply radiant and convection heat to develop interior texture and caramelization. Infrared sensors monitor surface temperature, and humidity sensors measure exhaust moisture for quality tracking. Exiting the oven, cookies pass onto a series of wire mesh cooling conveyors arranged in serpentine or spiral layouts. Ambient forced air circulates across multiple tiers to reduce cookie temperature from above 112 degrees to below 35 degrees within 8 to 12 minutes. Cooling speed is critical to avoid cracking or warping. Cooled cookies then enter a vision inspection system. High-speed cameras and image processing software detect dimensional conformity, color uniformity, chip distribution, and surface defects. Defective units are ejected via pneumatic actuators or diverter arms. Passing inspection, cookies are aligned into lanes via vibratory feeders and belt diverters. Lane alignment facilitates entry into the packaging system. Product counters track units per minute and signal robotic collators when batch quantities are ready. Packaging begins with slug loading. Cookies are grouped into vertical stacks, or horizontal slugs using indexing belts and pushers. Slug formation is synchronized with wrapper film feed using registration marks and encoder-driven rollers. Each cookie slug is pushed into a horizontal flow wrapper. Wrapping film is heat sealable and typically polypropylene based with a moisture barrier coating. The film unwinds from a roll and wraps around the cookie slug as it is propelled forward. Longitudinal and transverse heat sealers create the fin seal and end seals in rapid succession. Sealed packs exit the flow wrapper and pass under an inkjet coder that prints date codes and batch identification using edible grade ink. The print head operates in coordination with conveyor speed to maintain legibility. Wrapped packs are conveyed to cartoning machines. Here, cartons are formed from flat blanks by mechanical arms and glue stations. Wrapped slugs are side-loaded into open cartons, which are then closed, sealed, and printed with product and batch information. Cartons are grouped into shipping trays using automated case packers. These machines use robotic pick-and-place arms or pusher mechanisms to load cartons into corrugated cases. The case flaps are sealed using hot melt glue or tape applicators. Full cases move to a robotic palletizer station. Cases are arranged into a predetermined pallet pattern, layer by layer. Slip sheets may be added automatically between layers to improve load stability. Each layer is compressed slightly to ensure uniform height. Completed pallets are conveyed to a stretch wrapping station. A rotating arm or turntable applies plastic film under tension, with pre-stretch rollers ensuring optimal film usage and secure load containment. Wrapping cycles are adjusted for pallet height and weight. Each pallet receives a scannable barcode label printed by an industrial thermal printer. Labels are applied on two adjacent sides for redundancy. Pallet data is logged into the central warehouse system for tracking and inventory. Control. Ingredient replenishment is coordinated with automated inventory management. Raw material silos and liquid tanks are equipped with level sensors and integrated into the batch scheduling system. Ingredient usage is monitored in real time to prevent production interruptions. Throughout the production line, all mechanical systems are controlled by PLCs communicating through an industrial Ethernet network. Recipe parameters are stored in a central HMI interface, allowing operators to switch product types by loading preset programs. Mixing cycle parameters include motor torque, bowl rotation speed, and batch temperature. If values deviate from preset ranges, alarms are triggered, and production can be halted for correction. Chocolate chips are dispensed through vibratory feeders equipped with mass flow sensors. Feed rate is adjusted automatically to match dough throughput. Chips are gently folded into the dough using planetary paddles to preserve shape and prevent smearing. Extrusion depositors are cleaned and recalibrated between batches. Nozzle calibration uses laser measurement systems to verify uniform drop size across all channels. The baking oven includes thermal profiling tools, traveling temperature probes mounted on dummy cookies that measure time and temperature exposure across zones. These profiles are compared to standard references to ensure bake uniformity. Airflow in the cooling conveyor is managed by adjustable baffles and high-volume blowers. Zones are configured to prevent condensation or localized overheating, which could impact texture. Packaging film is spliced automatically using a festoon buffer system, allowing roll changes without stopping the wrapper. Splice detection sensors verify successful transfer and trigger rejection of the transition pack if required. Flow wrappers are equipped with film tracking systems using edge guide sensors to maintain alignment. Tension controllers manage unwind force to prevent film distortion. Cartoning machines feature vision systems that verify correct pack orientation before loading. Misoriented or missing packs trigger reject mechanisms that divert affected cartons to inspection lanes. Case packers use Delta-style robots with suction grippers or mechanical claws. Gripping pressure is adjustable to avoid crushing while maintaining speed. Robot arms operate on articulated joints with sub-millimeter precision. Palletizer systems incorporate automatic pallet dispensers and slip sheet feeders. Gripper heads are interchangeable for different case sizes and stacking formats. Production data, including line speed, output volume, defect rate, and downtime, is continuously recorded and transmitted to a manufacturing execution system. Reports are generated hourly for supervisory review and performance tracking. Temperature-sensitive ingredients, such as chocolate chips and syrup, are stored in climate-controlled zones. Delivery lines use nitrogen flushing or vacuum seals to prevent oxidation and contamination. Finished goods are staged in a climate-regulated buffer zone before loading. Inventory movement is tracked via RFID-tagged pallets, which interface with the logistics management software.